Next, SEMI is pleased to present a remarkable program on a remarkable subject in partnership with Applied Materials, a leader in materials engineering solutions used to produce virtually every chip and advanced display in the world. AI, artificial intelligence, is creating an exciting new era of growth in the semiconductor industry. It's also fueling a data explosion that will require orders of magnitude improvements in chip and system performance and power efficiency, as you saw John talk about earlier, far beyond what classic Moore's law scaling and von Neumann computing architectures can deliver. New breakthroughs will be needed, from materials to devices to systems. The AI design forum today will identify and propose solutions to the newest and biggest technology issues of our time. Our moderator for this exciting program is Applied Materials Corporate Vice President Joe Pond. Please help me welcome Joe to introduce the AI Design Forum. Thank you. Thanks, Joe. Here's your clicker.
Well, good morning. Well, as we heard in Dr. Kelly's keynote, the new era of artificial intelligence is going to require new computing architectures. And so without those new architectures, AI would quickly become unaffordable, and we would not be able to move into this era. So today, for our next session, we've assembled a really diverse panel of industry experts who are going to discuss system design and architecture techniques for AI. So I'm very pleased to introduce David Cantor. He's going to be the moderator of the panel. He'll come out and introduce his guests. David is a technical consultant on computer architecture, microprocessors, and machine learning. His past clients include AMD, Intel, and NVIDIA, Qualcomm, various investors. He previously co-founded a company pioneering a novel compute architecture, and he was a senior analyst at the Microprocessor Report. So please, let's welcome David Cantor and his panel.
Good morning, and thank you for joining us. I'm thrilled to be moderating this panel on system architecture. And I think, as the prior speakers have alluded to, in the absence of Dennard scaling and the slowing of Moore's law, we must turn to other places to get the performance to drive AI forward, to unlock the next generation of capabilities, whether it's self-driving cars, automatic diagnosis, or something we haven't even imagined yet. And system integration, system architecture, really encompasses everything from the lowest level process technologies, what metals you might use in your interconnect, your memory cells, all the way up to software and applications. And so it's a rich field, but given the slowdown in silicon, we must look elsewhere within system architecture to drive things forward. So that is going to be the focus of my panel. I have a number of wonderful speakers. But before we get started, I want to talk about one of the successes of the semiconductor industry, that is NAND flash, which is also sort of a potential example to learn about opportunities to improve system architecture. I think earlier one of these speakers mentioned that we're verging on $500 billion a year of semiconductor sales, and about 10% of that is NAND. So NAND is a huge economic success. It's in our iPhones, in our PCs, in nearly every application. But it was invented in 1987, and in the last 30 years, it has only very recently come to full fruition in the latest generations of phones and data centers. And over that time, we've improved the manufacturing tremendously. We now have both charge trapping and floating gate cells. We have multiple bits per cells. We have now moved from a simple planar NAND cell to stacking up vertically with 96 layers on a die in order to get better density. Looking a little further out from the flash, how we connect it into the system has changed. And initially, we treated flash as a hard drive and made it emulate spinning metal disks, and also emulate the form factor, which is fairly large. And that's clearly not the best way to use it. And it's only very recently, again, that we have had drives where we connect them into the system with an interface that is optimized for flash, where we have drives that are the size of our fingernails, which we can do with flash but could never do with hard drives. And it's only maybe within the last 5 to 10 years, that major operating systems such as Android, iOS, Linux, and Windows have out-of-the-box support for Flash and can take care of the idiosyncrasies of Flash. So, 30 years, huge economic success, but for us to move forward and deliver the performance we want, we don't have 30 years for the next set of innovations. So as new innovations roll out at whatever level of the stack, whether it is manufacturing, whether it is circuit design, architecture, or software, we should be thinking about, well, how can we get that into the hands of our customers in 3 years and not 30? So that is my charge to the industry. That is a challenge. Please think about it as you go on and about your day. And without further ado, I'd like to introduce my incredibly talented panelists. So first up, we have Kurt Busch, who is the CEO and founder of Syntiant, which is a company that specializes in doing analog inference engines using processing in memory. Next, we have Dr. Conrad James of Sandia National Laboratories, and he led the Hardware Acceleration of Adaptive Neural Algorithms challenge, and they were also working on novel memory techniques and advanced algorithms. Dr. Dilip Bhandarkar, currently retired, but formerly of formerly of Qualcomm and Microsoft. At Qualcomm, he led the server group from a technology standpoint, and then previously was a distinguished engineer at Microsoft, where he helped build out the hardware infrastructure that powers Azure. Gary Lauterbach is the CTO and co-founder of Cerebras Systems, which is a startup that works in machine learning. Previously, he was the co-founder and CTO of SeaMicro, which pioneered low-power server technologies and was acquired by AMD. And before that, he led development of high-performance processors at Sun and AMD. And last, we have Bhuvna Ayagari Sangamali. She recently joined Applied Materials after more than 15 years at Synopsys, where she led engineering for the interface IP business. And prior to that, she was at Intel working on mobile and desktop CPUs and chipsets. So please give us a round of applause for the speakers, and thank you them for joining us. So the title of this panel is The Memory Wall, Overcoming the Memory Wall. So I guess I'd like to start with, I think, Gary and Dilip. Maybe Gary, what to you is the memory wall, and what are the challenges, and how should we think about it?
Sure. I'd like to take a minute and talk about an example. The traditional memory wall, as I see it on a normal CPU, let's take an example of running one operation per cycle on a gigahertz CPU. Nominally, there's about 20% memory references. It results in a 200 million long sequential memory access chain that's completely bound by the latency of those memory operations. Contrast that to a neural network. If we look at ResNet 50 as an example, there's about 50 sequential layers, a total of 4 billion operations for a single forward inference. This results in a parallelism of memory of 100 million, order 100 million memory operations as the limit. Performing those 100 million memory operations concurrently, which is certainly possible, has great implications on both architecture and energy forward-looking. This, to me, is a vast difference between the traditional memory wall, which is strictly latency-bound, and the neural network AI memory wall, which is strictly bandwidth-bound, energy-bound. We're going to see the implications of this played out in the next few years in architecture and implementation.
Let's talk about where the term memory wall came about. I think we started noticing in the early 90s that while CPU performance was growing at a rate of about 50% per year, memory performance measured in terms of bandwidth and latency was only in a 10%-ish improvement. And in 1995, Sally McKee and Bill Wolf wrote a paper coining the term memory wall. So the memory wall was limiting overall system performance, even though CPUs were moving faster. To build upon what Gary just said, there are a number of ways that you can address this. For example, larger scratchpad memories on the SoC, reusing data so you're not accessing the same information. Compression is another technique. So there are many techniques that in a machine learning SoC you can use, and maybe some new technologies like, for example, MRAM could be useful if we can get higher capacities at lower power and therefore reduce the amount of time you have to go off chip to really slow DRAM.
Anyone else?
Just like to point out that one of the things that when we founded Sentient was really to overcome this limitation in memory, and as opposed to just going with traditional compute architectures, the memory wall is actually quite dominant in machine learning, as Gary pointed out, is that we are doing complete computation in memory. So we don't just kind of reduce the memory aspect of this, but we completely eliminate it. And by doing computation in memory, both the way Sentient is doing and other people are doing it, we can eliminate this kind of memory bandwidth and power constraints.
So I think that actually brings up an excellent question, which is, as we've seen the gap between SRAM and DRAM and flash widen, what sort of roles do you see that new memory technologies might be able to play in this? Anyone want to tackle that?
I think it comes down basically to power and economics. If there's a new memory technology that is more economically viable in terms of what it costs to get a certain amount of capacity and at low power, and it can be done using a standard process that's being used for the rest of the chip design and not some exotic process that adds cost eventually, then those new memory technologies become viable. So it's not just the technology, but it's also the economics associated with it.
Yeah, I would agree with that. And second what Kurt said, that it's really important to integrate the memory into the compute to save energy, to get the energy low enough to perform this vast number of memory operations in parallel. You need tight integration. If you have to go off chip, the energy cost is just prohibitive.
And many of the new, well, as we go down the process curve, current technologies for non-volatile memory, such as flash, are kind of running out of gas. So new things like MRAM or ReRAM or things along those lines give us hope that we can still use non-volatile memories as we go down the process curve. And then much of the new technologies are just adding additional layers on top of the chip, which not only gives you nice performance, but it also can reduce the die area cost, which is a nice adder for these kind of new memory technologies. So I really think that with machine learning, a lot of these things will be adopted over the next coming years.
And just briefly to add to that, I think that the industry understands that machine learning is a true paradigm shift in terms of how computing is actually being performed. Explicit programming, where you have the equations and you know exactly what you're trying to calculate, is very different from machine learning, where you're essentially using data to train your system or to train your algorithm. So it's much more energy intensive, it requires lots of data, lots of operations, and so looking at new technologies that can really drive that energy requirement down is something that we definitely need to develop.
Now, Conrad, within your group, I believe in some of the research you did, you looked at novel algorithms and sort of things that we can use to empower them. Can you maybe speak a little bit to that?
Yeah, so I think that machine learning has an incredibly interesting history, going back 100 years to the first McCulloch pit neuron, which was very simple, could not really be trained, but was useful for some very simple computations. That then evolved into the perceptron, which was more complicated, could be trained, and could actually solve some again, very simple problems. In the 50s, we saw some of the limitations of the perceptron from a calculation standpoint, and the mathematical analysis of that sort of led to the first winter in machine learning. Over the years, we started to develop new approaches and algorithms, the multi-layer perceptron, which overcame some of those mathematical limitations. And now we started to see a little bit more promise in terms of how machine learning and AI could actually solve more complicated problems. That still led to another sort of lots of promises that were not being fulfilled. That led to a second AI winner. And so now we're in the sort of third wave of machine learning and AI, where now we're talking about deep neural networks and convolutional neural networks, which are much more complicated and are now actually solving real problems that we face every day. And so I think that the trajectory of developing new algorithms that actually help us to solve these complicated problems and meet the challenges of the 21st century has really led to this explosion. And we've leveraged a lot of what has occurred in silicon, developments with GPUs, new architectures, ASICs, FPGAs, but I still think that we need to continue to look at algorithm development to really understand how the data is being transformed. I think one of the challenges that we face in machine learning is that we know how to build these systems, but we still don't quite understand how they actually work. It's sort of the opposite problem from quantum computing, where we understand the math, we understand the physics, but it's hard to build. It's hard to implement. Same sort of issue with exotic computational approaches like reversible computing. We understand the math and the physics, but we don't know quite how to build it. With machine learning, we know how to build it, but we still don't understand how they actually work, how the data is transformed. And so a lot of the groups around the world, both academic as well as industry, are starting to develop techniques so that we understand how the data is being transformed, and that, I think, will continue to lead to lots of innovations in this area.
Gotcha. So I actually have a question in that vein for Bhuvana. We just talked about algorithms, which is certainly one aspect of system architecture. But Bhuvana, where do you see the next big innovation happening to meet the requirements for new compute in AI? Is that going to be in process flow, in EDA, in system architecture, maybe a new device like a FinFET, or some combination thereof?
It's going to be a combination of all of those. So if you look at the innovations that are happening today and the requirements of artificial intelligence, so it requires very data-intensive computations in almost real time at the edge. So this means very high performance and energy efficiency. So if you look at the innovations all the way from materials, process, there's a lot of innovations, but there is no single knob that gives you meets these challenges and meets these requirements. So on the material side, you have innovations. Then you have on the process side, whether it's patterning or litho or selective deposition, any of those techniques, they are all giving you incremental benefits. Come to EDA, there's automation happening in EDA and new design techniques in order to realize these designs. But at the end of it, no single knob is giving you all the benefits. So really what needs to happen is accelerate the innovations that are going from process to design. DTCO, or design technology co-optimization, is a concept that has existed for a while. But really what needs to happen here is accelerating that. And which one of these innovations is going to give you the most ROI? Which one is going to translate to the best performance or power that's required, which is going to give you the most energy efficiency? So those are the questions that need to be answered and answered rapidly. So what needs to happen there is acceleration of DTCO, which in turn requires more collaboration across the ecosystem, all the way from materials, process, EDA, design, all the way up to architecture.
So I think one of the things that both of you touched on a little bit is, things are very much in flux. And I think that brings us to a great question, which is about programmability. And one of the challenges with neural networks is, as everyone has said, they're changing rapidly. I think 3 or 4 years ago, there was no such thing as the generative adversarial network. What you might use to, say, generate a photo based on historical photos of me. That didn't exist up until recently. So I guess for Kurt, how do you think about the trade-off between programmability and fixed function? And I know you have an analog accelerator. What sort of drove that design corner?
Sure. So the whole idea about programmability and more fixed functions, I really see as a one-to-many or a many-to-one problem. So in this case, the one would be a processor that would be in the cloud, and a many would be something that was on the edge. The processor in the cloud has to service many different types of devices, different kinds of workloads, different sorts of things. So the device in the cloud has to maintain a high degree of programmability, while the devices that are the mini, which are the ones that would be up on the edge, and the farther on the edge it would be, the more limited programmability is really required, and then if we extend that all the way down to something that would say be in a sensor, it probably doesn't need to have very much programmability at all. So it's really kind of this continuum of things that are on the edge require small amounts of programmability, and devices in the cloud require large amounts of programmability.
Gary? Any thoughts?
Certainly, cloud-based devices have to be very flexible, programmable, because forward-looking, there's a lot of innovation still possible in network topology, algorithms.
I think the answer is a combination of fixed function. Fixed function things are likely to be much more efficient from an area and energy efficiency, but it also limits you. So some combination, the right mix of fixed function and programmability. I spent the last almost year talking to some of the large cloud service providers on what they thought they needed in an inference accelerator. And one of the answers was from all of them is that they, like I think David said before, this whole thing is in a state of flux. Nobody knows exactly what you're going to need. So if there's going to be, if you can provide some programmability, that would help a lot. So the design that my team came up with was a combination of matrix units, fixed functions, combined with a RISC-V core with vector extensions. And it was my belief that combination would have worked well, but that was a research project. My employer decided not to build that device, fine. But I think those are the kinds of things I think you'll start seeing people deploying, some combination of the two.
And so for Conrad, actually, one of the questions I had for you was that we talked about briefly is, today if you think about typical architectures, your front-end sensing, whether it's an image sensor for a camera or a pressure sensor or whatever, is wholly separate from the analytics. And you go through A to D conversion, and then you might clean up your data. For if it's visual data, you may do debayering. Do you think that there's a possibility that we might want to look at fusing the two on the inference side?
I definitely think that is one of the next innovations that will come to the industry. Thinking about how sensors acquire information, transform that information, and then starting to develop architectures that are closer to the sensors so that we have less loss, so that there's less information lost, there's less power consumed. I think that's a smart way to start thinking about this. It does remain a challenge, though, in terms of figuring out ways to have these heterofunctional systems where you have a sensor and then you have your processing, and trying to bring those closer together certainly brings to bear some of the engineering challenges that the industry has faced in other modalities. So I certainly hope that the industry will move in that direction, and I think it's certainly an area that's rich with opportunities at this point.
Gotcha. So speaking of opportunities, I was actually at a talk not too long ago from Andy Bechtolsheim. And one of the things he said is that, generally speaking, many of these large cloud companies have seen about a 10x improvement in neural network performance over the last couple of years. So Gary, as you're looking out, how much more do you think we can drive that before we run into whatever limits?
So going back to my example of ResNet 50, there's order 100 million parallelism available, fine grain model parallelism. Today, GPUs leverage about 10,000x of that, so we have an order 10,000x left to mine. So to quote Richard Feynman, I'd say there's plenty of room at the bottom.
And what about other folks?
Yeah, so our focus is really been, as the previous speaker from IBM was talking about, is taking new architectures to solve neural networking inference problems. And by looking at analog neural networks, basically with reduced precision and massively parallel networks, we think we can get in our first generation process like another 50x above and beyond what is going on today. And then after that, we still have some way to go before we hit the quantum limit for this kind of electronics. So I think that by using clean sheets of paper, whether it's something that is for an inference device or a training device, we can basically break free from kind of this boundaries of CPUs and GPUs that really got us where we are today. But the answer for greater efficiency is going to be some kind of new processor.
So since this is a semiconductor conference, let me give you a data point. If I were to design an inference accelerator in 7 nanometer today, I think I know how to, or not I think, I know how to deliver 100 teraops at less than 10 watts. Mm-hmm. That is where the technology is today. How that maps into the 10x that you mentioned, David, I don't know. But that's sort of a state of the art in a chip that's less than 200 millimeters squared. So that's where the technology is today, and I'm talking about ResNet kind of networks. Yeah. And you can extrapolate from that if you want.
Yeah. And actually, the process technology point is a fantastic one. So, if I recall correctly, Kurt, your process technology is relatively older, and so you might have reasonable room to drive down to a smaller technology once they become, suitably characterized and analog friendly, right?
Yeah, absolutely. So we're doing analog computation in Flash, and we're using a 40 nanometer process, and that process today in our first generation chip is a 20 teraops per watt device. So it's a pretty efficient device in a relatively older process. So we do have a lot of room to grow. And our thought was 20 tops per watt was a pretty good number to stop at. I mean, at some point you have to tell the engineers to stop innovating, and we actually have to build the product. So we're pretty excited about what we'll do for the next couple of generations.
Now, in the vein of process technology, Dilip, when you were at Qualcomm, I think one of the taglines of the Centriq processor was it was the first 10 nanometer processor. So you're clearly an evangelist of advanced process technologies, and
yes, I am. I believe that the more newer nodes give you better performance, lower power, and lower area. But something that I hadn't fully comprehended until I talked to Jan yesterday is that some of these transitions come at a high cost. We all talk about PPA, power, performance, and area, but what has happened as we moved from 28 to 16 to 10 and 7, that the wafer costs have gone up tremendously. And I don't have the exact data of how much they've gone up by, and the throughput has increased. Like today on the 10 and 7, from tape out to first silicon is more than 4 months. So if I'm doing an SoC, I can do the basic design of the SoC in 6 to 9 months, but if I have to have 2 spins, that adds another 9 months to the process, and then so I'm talking about a design cycle of about 2 years. So how do I predict what's going to be needed 2 years from now? So I think we need to start thinking about the cost. And and today, if you look at where we are, TSMC is in production with 7 nanometer. I'm not sure if anybody else is. And another large semiconductor company that I worked for in my past is struggling at 10 nanometers. So, what's going to happen at 5 nanometer? Is there a cost-effective way of delivering lower cost per transistor at 5 nanometer using EUV? Yes, the technology is there, but what's the cost and the throughput time associated with it? I mean, we as engineers like to think about the physics, but the economics and just the throughput time is equally important.
Yeah,
So I'm getting a little less enthusiastic about the latest node, and I can see why. A lot of companies are still on 28 nanometers because even though the area is higher, the power may be slightly higher, economically it makes sense. And for a large company like a Qualcomm, getting to 10 nanometers, given that we were doing it for the smartphones, we were able to ride that curve for our server products. And the same with 7. Our next generation would have been in 7. But that doesn't apply to the industry at large.
Yeah, to add to Dilip's point, so precisely, right, we're not getting the benefits from pure technology node scaling because it comes at a very high cost, whether it's longer design cycles or yield or some other problem. So the answer really needs to be beyond just technology scaling in order to achieve these performance and energy efficient devices for different types of computes. If it is not purely in technology scaling, where else can we look? So we need to look all the way across the ecosystem, from materials, the process innovations, all the way up the stack to the architectures. So right in the middle of this bridge from process and technology to compute architectures is actually design and EDA. And so how do we bridge this gap going from the innovations that are happening in materials or process to architectures? So there are 2 specific things, in addition to the problems that Dilip stated. For EDA and IP vendors, this means that having all these choices of nodes and nodelets and half nodes and suffix nodes means that they have to provide reference methodologies, reference designs, and IP qualified at all of these different nodes. So that is a challenge for them. And also, the concept of DTCO, again, how do you accelerate this? The 2 specific problems that we need to solve in this arena is, first of all, more automation in EDA, in design methodologies. There is automation already available, so the concept of machine learning, the concept of auto routers and placement and routing, the concept of optimized synthesis has existed for a long time. What needs to improve there is really accelerating all of these, and via DTCO, again, making the choices and the ROI options available faster, accelerating that via more automation and DTCO.
Anyone else have anything to add in that vein? All right. Yeah, so actually, I think another question for Gary and maybe the other panelists as well. In terms of technologies that we can use, which ones do you think are going to be the sort of greatest ROI for neural network accelerators of the future?
I think given the parallelism potential of the workload, there's a great opportunity in packaging. We shouldn't limit ourselves to single die silicon. With innovative packaging, it's possible to manage the energy used for both the compute, the communication, and memory access. And packaging has, I think, great potential going forward to overcome what we see as a brick wall in Dennard scaling.
I think it's going to be a combination, again, packaging definitely, but also we talked earlier about the different types of memories, new memories that are emerging. MRAM, for example, STT-MRAM shows some promise. The characteristics that it has in terms of the write currents, the write access times, and also the fact that it's compatible with back-end of line process. There's a lot of promise there. And again, how do we bring all of these to fruition rapidly is accelerating the prototyping cycles, the DTCOs, making those faster, making it less expensive to go through these iterations on the various innovations. It all has to come together, which means, again, collaborating across the ecosystem.
I think we need high-performance multi-chip packaging. Most of the solutions that exist today are not high performance. There's too much delay going from one chip to the other. And the other nice thing about multi-chip packaging is you can mix technologies. That it doesn't all have to be, maybe for the compute part, it's a leading edge node. Maybe for the memory, it's something else. Maybe for the network. So it allows you to have a heterogeneous mix. But I haven't seen any multi-chip packaging technologies that I'm happy with in terms of cost and performance. So that's an area of innovation I think is worth investing in.
And I think we also need developments and innovation in photonics, chip-to-chip communication, coming up with new ideas to drop that energy consumption that goes as you're moving data from one chip to another. I certainly think that those are areas that we need to continue to invest in as well.
Yeah, and I think both the photonics and the packaging really fall into the buckets of trying to avoid fighting physics, right? And as we're able to bring things together in the package, in many cases, communication and moving data around simply dominates computing. So if we get things, only micrometers away instead of millimeters, that's a huge win.
So let me correct something I said. I think the best multi-chip packaging I've seen is Intel's EMIB.
Yeah.
But that's not available to the rest of the industry.
I hear there's an opening at Intel these days, Dilip. Maybe you should throw your hat in the ring.
I'm not CEO material.
So actually, for Kurt, in terms of multi-packaging technologies, do you think that might make sort of the analog integration easier as you look at sort of more and broader products?
Yeah, actually, I think Dilip really hit it on the head, though, is that at least I see the biggest advantage to multi-chip packaging is that you do compute in an advanced node that may take several years to develop. Then you could do basically auxiliary functions, maybe a neural network accelerator, maybe this, maybe that could be in a different node and package them all up into a single chip. And that could greatly reduce the cost of coming out with new chips. You could come out with a new chip every year, maybe every 6 months, with dramatically different performance and attributes to really address the product market fit for that particular application. If you have to do everything in, say, 7 or 10 nanometer, you're looking at hundreds of millions of dollars in a couple of years, and it really just doesn't let you be as agile as you need to be in a fast-growing market that we've lived in technology for last up 10 years.
Yeah. So here's an interesting question, and take it for maybe start with Conrad, but as we look at different types of neural networks today, our convolutional neural networks that we use for video have very different compute, memory, and communication patterns than, say, a recurrent neural network or a multi-layer perceptron. At what point, and this goes, I think, for everyone, do you think that we might choose to specialize in and have different flavors of accelerators for different flavors of neural networks?
So I think we have to remain flexible, and the ecosystem of machine learning is incredibly diverse right now. As you mentioned, we've got recurrent neural networks, convolutional neural networks, deep neural networks. We have different learning mechanisms that innovators are trying. So we're still in this sort of Edisonian stage of trying a bunch of different techniques and methods to solve different problems. And so thinking about this from a sort of a learning standpoint, you've got unsupervised learning where you really don't have any sort of output that is telling you whether or not your algorithm is working. So you're just putting in inputs. And then you have reinforcement learning where you're providing some sort of a modality that's telling the network whether it's working well or not. And then you have full supervised learning. So you have all these three different modalities. And I think having accelerators that can attack either of them or all of them is really where the industry needs to stay.
So that's a call for sort of general purpose acceleration.
And I think I'll
Possible.
probably, take a little bit different view. I really look at this as a business problem, not necessarily a technology problem. Is that it's fairly easy to build chips that can do multiple types of neural networks, but if you have an application that's going to ship 100, let's say 100 billion units, and you need to save $1 off of that, and you can make a hardened chip that will do that, then that typically says, okay, you should actually build that chip. So I think this is not so much a philosophical idea about what I'm going to do in neural networking research, or I'm going to actually build flexible or fixed chips. It's more of a decision about what is the chip you're building. Are you building an ASSP that sells 100 million units? Or are you building some general purpose processor that may sell 100,000 units? And it's really just a give or take based on what the economics and the business proposition. Much more of I'd say, applied deep learning as opposed to more theoretical deep learning.
I think you're both correct, because if you had an application that is high volume, clearly you should specialize for it. But to Conrad's point also, there's a wide range of applications that are not high volume. And in that case, having something that's more general purpose with programmability that allows you to tailor on the fly to address a variety of different things that individually may not be as high volume as the one that you're talking about. So yes, you're both correct in that for something that's known to be high volume, specialization makes sense, but something that's sort of in the middle, then a more general purpose with programmability seems to me to be the right answer.
All right. So as we're beginning to approach the end of the panel, I think we have about 4 minutes left. I'd like to ask each one of the panelists, so what is the top 1 or 2 item on your process technology and manufacturing wish list? You find Aladdin's magic process technology lamp in a disused fab. You rub it and it says, I'm going to solve this problem for you. What do you say?
Oh, you're looking at me to start? Let's ladies first.
All right. So mine is probably more of a pet peeve than a wish list. So going back to Dileep's point again, right? Yes, we're getting some performance and power benefits as we scale down, but just look at how long that takes, right? And look at, again, the number of options you have in terms of nodes and the amount of confusion, nodes, nodelets, suffix nodes, et cetera. I think we need to start standardizing on those. So one of the complications there is also the design rules. So those need to be standardized. We need to come up with collaborative schemes where we can accelerate the prototyping cycle so that we get through these designs faster and in a less expensive way.
I only want denser, lower power memory. I'd be happy with that.
So I'm going to speak from a point of somebody who consumes technology and not somebody who delivers it. We talk about PPA, performance, power, and area. I want to add cost to this. I don't care what the materials are, what the process technology is, what the tools are. Give me something that is significant in all 4 of those vectors, and I'll be happy.
I'd say we need to develop processes, devices, architectures that are better suited for training. I think that's the big hump that machine learning faces right now. It's much more difficult to train, especially if you're talking about a deployed system that needs to be trained while it's in the field. And so any type of technology that would help drop those training costs, I think, is what I'd like.
So I'd like to take a little different spin of these things, is that we've talked for the last a little over half an hour about innovation and process technology, but one of the sad truths about cutting edge process technology is it is really expensive. I mean, I think Gartner Group said that a 7 nanometer development is north of $200 million. That is an expense, that's a check to write that very few companies can write. And we are looking about innovation. Everyone talks about innovation. It's probably the most overused word in our industry. And innovation comes from startups. And startups can't afford to write a $200 million check. Maybe Cerebrus, but maybe, but most of us can't. And my request actually to the industry would be, how can you access these advanced process technologies and really allow startups to do it? Because today it's only the monster companies, it's the Intels, the Qualcomms, the NVIDIAs that have access to these technologies, when instead, if you want to drive true innovation, get 100 people driving these technologies and they'll come up with something quite interesting and quite innovative.
All right. Well, so I think we have a minute to go. So one last question. So today, the current paradigm is really we train in the data center, and then we perform inference in the edge and in the data center, and it sort of depends on a wide variety of things. If we look out 5 to 10 years, do you think training will be edge, data center, both?
So I'll start. I actually think absolutely that we'll see training in the edge. Today, train in the data center and inference on the edge looks good. I think that 5 years from now, it's not that far away, so we'll start seeing some training on the edge. Likely, I believe the major parts, let's say the first several layers, will be trained in the data center, and then we'll have a last couple of layers that will be trained in the edge, and we'll start seeing adaptive types things in the edge. And I think that's really inevitable, and as time goes by, we'll see more and more kind of adaptive activity in edge devices.
Now, let me add to that. It's not just the data center edge. I'll go further and say it's also quite likely 5 years from now that there will be enough compute power in your smartphone, and some amount of training could be done even in the smartphone. So it's smartphone, edge, and data center. I guess I used to work for Qualcomm, so I got to give a plug for the smartphones.
He still probably owns some stock. All right, well, I think that's enough time for our panel, so on to the next stage. And thank you guys and lady very much for sharing your wisdom and time. So let's give the panel a hand.
Thank you to all our panelists. It's a great start to the forum. I don't think the memory wall looks nearly as daunting as it did about 45 minutes ago. So one of our goals today is to provide you with a new perspective on the future. And our next speaker is definitely someone who has a perspective and a point of view. He was just named by Barron's for the second year in a row as one of the world's best CEOs. Gary Dickerson has a unique ability to spot technology inflections and then mobilize a company the size of Applied Materials to run off and make possible the innovations that shape the future. And the next big inflection that Gary has spotted is AI, and he and Applied Materials are grabbing that challenge and running with it. So please welcome the president and CEO of Applied Materials, Gary Dickerson.
It's really a pleasure to co-host today's event. When we were talking to people about the event, we had tremendous pull for participation. Really, this is the biggest inflection in all of our lives. And the great thing for Applied Materials and everyone in this ecosystem is that we're at the beginning of the first inning of this major inflection. I'll talk about the opportunities, but there are also tremendous challenges. And the one thing for sure that we all love is to tackle those challenges, and I'll give some thoughts about how we're going to do that. So, you've heard today about the opportunity, and really, technology is positioned to transform major industries, many, many different parts of our lives, democratizing healthcare, transportation, many, many different areas are fundamentally going to be transformed over the next decade, and that's going to create tremendous economic value. In the last century, oil fueled the Industrial Revolution, and now it's data fueling this AI, big data revolution. So the opportunity to turn that data into actionable insight is worth trillions of dollars. But as you've heard today, there are significant challenges, really to realize that multi-trillion dollar opportunity. So I'm going to go through that today, talk about that today. So in AI and big data, you have on the edge data generation. Then you're storing that data. You have to store that data in a cost-effective way, and then processing the data. Oil sitting in a barrel in the last century wasn't worth much until it was processed. So processing is very important, and of course, connecting all of those things together is very, very important. So we already see in our business, in our industry, growth in all of these different areas, but really, again, to unlock the value, unlock the potential of AI and big data, we have to drive significant innovation. And I'm going to cover that around these different topics here today. So if you look at data generation, what's happening with data generation? Data is exploding. Everything is becoming smarter. And if you also look at what's happening, if you look at data generated from humans versus data generated from everything else, we hit an inflection point where in 2018, for the first time, machine data is greater than human data. And John Kelly talked about many of the areas where AI and big data are going to have a major impact from an industrial perspective. But what you see going forward is just an explosion of data around the edge with all the IoT and smart devices. And again, most of that not being generated by people. So, and when you think about it, in autonomous vehicles or in smart vehicles, you have 6 to 8 high-definition cameras, you have LiDAR, and it's constantly generating data. So this explosion of data is happening. It's already having positive impacts in our business, but we're really still in the early inning of this major inflection. So AI is older than Moore's Law. And one question is really, why is this happening now? Why is AI and big data growing so fast and poised to really transform major industries? And we're already seeing impacts in a number of different areas. Well, with AI and big data, you have to be able to store a lot of data, and the size of the data set matters. If I have 100 data points versus 100 million data points, my ability to make determinations and decisions is much, much better. So having storage capability at the right cost is certainly critically important. And then high-performance computing for the relentless classification of data to make determinations and predictions. And the last panel talked about accelerator technology and AI workloads. So what you need is a lot of memory and parallel computing. So if you look at x86 and ARM architecture CPUs, they're really good for general computing, but the accelerators that are really winning today, TPUs and GPUs, are parallel computing and designed for high throughput. So those areas are growing extremely fast today. But when we talk to leading compute companies, what they say is that we still have a 1,000x gap to where we need to go in performance per watt. Performance per watt and cost. So John Kelly talked about the world's fastest supercomputer earlier today, which was a tremendous innovation, but the power consumption is much as a small city. So the challenge for all of us in this ecosystem and in this industry is really to tackle the gaps that we have here today to enable the multi-trillion-dollar opportunity for the entire industry, to unlock that value. And another thing, when I talk to investors and I ask them, what is it worth to have the winning AI chip 12 months ahead of anyone else? Consistently, the answer I get back is $100 billion. So what we're driving inside of Applied Materials and what is so important is speed and time to market. John talked about also the first person to enable those inflections is the winner, and the other people are disrupted. So again, within our company, what I focus on is $100 billion. What is 1 month worth? What is 1 minute worth? It's super important to accelerate these technologies to unlock value for all of us and also shape a better future. So solving gaps faster than others is extremely valuable. So what's happening today, you have the current accelerator technologies, but there's still gaps to where we need to go in power, performance, area, and cost. And you see focus across the ecosystem on many different chip technologies. And there's more. Hardware is becoming sexy again. People are focused on hardware. In the last 18 months, there's been more money going into chip startups than there were the previous 18 years. So tremendous focus, and this is from traditional companies in compute, startup companies in compute, software companies more focused on hardware. So tremendous focus on innovation. And I deeply believe we're not going to get where we need to go doing what we've done in the past. And I'll talk about some thoughts around the ecosystem of some things that we're driving within Applied to support and accelerate this innovation. So we need 1,000x improvement in performance per watt. AI needs innovation in the edge and in the cloud, and generating data on the edge, storing the data, processing that data to unlock the value. At the same time, Moore's law is slowing. So when you think about this, you could say this is a perfect storm. Is this the perfect storm or a perfect opportunity? And certainly, within Applied Materials, I deeply believe, and I passionately believe, it's the perfect opportunity. It's a great opportunity for us to innovate in different ways. So, Moore's law. Moore's law created tremendous economic value, changed the world in fundamental ways. And so if you look at the charts here on the left, you have figure 1, which is a very famous chart from Gordon Moore. On the right, you have 5 data points on a log scale. And basically what this says is that the number of components per chip is doubling every 2 years. So taking those 5 data points and extrapolating it, let's look at what happened over the next 40 years. And basically what you see is that projection held. Incredible innovation, incredible value this industry delivered to the world. 2x increase in transistors every 2 years for 40 years, created tremendous value and changed people's lives in fundamental ways. But what's been happening here recently? So this is data from 2 leading logic companies. And if you look at what's happening now, that is slowing down. So instead of doubling every 2 years, it's doubling every 5 years. So fundamental challenges. And again, we have a 1,000x gap in performance per watt that we have to close. So more charts on the rate of improvement. Chart on the left is from a book called Computer Architecture Bible, written by David Patterson, a professor from Berkeley and now at Google, and John Hennessy, a professor from Stanford. Dave Patterson will be talking later today. And the chart on the right is from a leading research firm and also showing the time between technology nodes is slowing. So you had all of these different charts basically showing you the rate of improvement is slowing. At the same time, the value of technology to disrupt major industries has never been better. So that's really the challenge for all of us, is how do we make this happen? How do we overcome these challenges? In the past, Moore's law was driven by classic 2D shrinking and materials engineering to drive power and performance. And again, the last panel talked about power, performance, but also area and cost simultaneously driving all of these different key parameters is really important for us to unlock the value of AI and big data. So what's the future look like in driving PPAC? It's really about enabling new structures, new architectures, 3D structures, new materials, new ways to shrink, and advanced packaging. All of those areas, there's tremendous line of sight to innovations in every one of these different areas to close that gap. And what's exciting for us at Applied Materials is that the foundation of all of this is materials innovation. Are these new structures? Are these new materials? All of these new capabilities. And we're driving with high speed across the entire company in all of these different areas. So let's look at some examples of materials-enabled scaling. So one of the best examples is 2D to 3D NAND. So 2D NAND, there was a playbook that was there for decades. And the playbook was about shrinking in 2 dimensions. So what happened? What happened when that playbook ran out of gas? When the electrons in the memory cell were getting less and less, cost per bit was leveling off, performance was being challenged because of physical limitations. The industry innovated and went to 3-dimensional structures. That was all about materials-enabled scaling. And when I think about, and I'm tremendously confident, cost per bit is going to continue to go down. We have a decade-long opportunity to continue to drive scaling. There's innovations that people aren't aware of today that will happen in memory to continue to drive this innovation. But it's around materials-enabled scaling. And really, when I think about going in the 3rd dimension, the sky's the limit in how far we can go in cost per bit and performance with this other thinking. But again, you have to think differently, away from 2D scaling to 3D scaling with these different technologies. So I'll give you another example. This is showing, for the technical people in the audience, this is a polygate. And what you're doing when you're scaling density, number of transistors, over time, you're shrinking those transistors. And the ideal case is that when I'm shrinking those transistors and I'm not using them, they're off, I'm not leaking any power. That's the ideal case. But what happens from a practical perspective, this is a graph where you see technology nodes along the x-axis and leakage current, think about this as power lost, along the y-axis. And what you see is that you have a polygate. Every technology node, you're shrinking those transistors, and leakage current is going up. Power is being lost. And that's not a good thing. That is not a good thing. So what happens? What happens is we drive innovation in the structure. So we go from polygate to metal gate, 4 orders of magnitude reduction in leakage current. So what's happening with metal gate? Again, you're shrinking those structures. And every technology node, leakage current is increasing. So within Applied Materials, we're driving innovation in many different areas. This is one of those areas. So in our labs, we have capabilities to innovate and enable another 3 order of magnitude reduction in leakage current. And I'll tell you why I'm also so excited. I'm excited because being able to build these new structures, we have clear line of sight in the wiring of a device. You drive speed, drive current, but how much is lost in the resistance? We have innovative structures to solve those problems. Edge placement. I can have a shorter wavelength and resolve a smaller feature, but where are those features placed on a chip is one of the biggest challenges of the industry. And everyone is focused on self-aligned processes. And that requires innovation. That requires materials innovation. We have line of sight to those types of technologies. Driving performance, driving packaging innovation, all of those areas I listed earlier, a clear line of sight to innovations in all of these different areas. So those are a couple of different examples of materials innovation. And if you look at the amount of materials that are being used in semiconductor processes for future processes, it's exploding. The number of materials are exploding. And it even goes beyond the periodic table of elements. If you look at the types of carbon, the types of silicon oxide or silicon nitride, there are many, many, many different compositions of materials. Some of them are driving electrical performance, but some of them are also necessary to build structures that aren't possible today with innovative technologies. So this is exploding, and it's enabling different ways to build a device. So we have challenges, 1000x gap. We have a phenomenal opportunity, and really new playbooks are needed to drive innovation. And certainly within Applied over the last 2 years, we've been driving fundamental changes within Applied Materials. Connectivity and speed. I've already talked about speed, $100 billion for 12 months. Speed is super important. But connectivity, solving these problems faster, requires all of us to think differently, to structure differently, to focus differently, to connect differently in the ecosystem. So I'll give you one example. 3 weeks ago, I spent, in 1 week, multiple hours with the leaders of R&D of our top 3 customers. 3 different meetings, 3 different places. And when I'm talking to them, one of the leaders had told me, he said, "Gary, this one material is really great electrically, but I can't integrate it into a structure. I can't planarize it. I can't remove it." Now, the fact he's telling me that, they don't tell many people about those material choices and what the issues are. And why are they telling Applied Materials that? They're telling us that because we know how to planarize structures. We know how to remove structures. We can modify structures with treatments broader than anyone else. We can create materials that many others can't create. And it's all about speed. It's really from moving from unit process optimization. I can create a material, now I'm going to focus upstream or I'm going to focus downstream, to how do I optimize all of this in parallel for integration and speed. This is really, really important. $100 billion for 12 months. Time is very valuable. So this parallel optimization, going beyond the unit process, we're seeing stronger pull for that than we've ever seen it before. And a really, really great opportunity for Applied to engage across the entire ecosystem. So here's one example of an integrated process. So you have on one side a unit process platform, and on the other side an integrated process platform where you're combining 4 different technologies in a single platform, and only Applied has this capability. And why is this important? Why this is important is because the interfaces between all of these materials in building these unique structures are becoming more and more critical. If you can't manage the interface engineering, you can't enable a structure with lower power. So again, that is really, really important. This is an example with Cobalt in the wiring of a device, but we have many capabilities, innovative capabilities that we've developed beyond this particular example, and tremendous pull from customers living in our lab in the Maydan Technology Center full-time enabling these new structures. Okay. So, when we think about connectivity, what I have here on this graph is a von Neumann type of mindset, serial mindset, and a neuromorphic mindset. So the thing that I've come to realize over the last 2 years is what I don't know. And there are degrees of separation between what we're capable of delivering and what actually makes it into a device. And I deeply believe it's too slow. So if we can innovate with a fully self-aligned structure that solves edge placement errors, or we can make significant improvements, orders of magnitudes improvement in leakage current or resistance or any of these different areas, we have an understanding of that, but getting that information to a designer, again, in many cases we speak different languages, and that connection is just too slow. So again, that's a big focus and a big opportunity, is to drive this connected parallel mindset. Speed is valuable. And again, this is an area that we're focused on. And I think for the whole ecosystem, this is a great opportunity. So, within Applied Materials, we're driving fundamental changes. It's the best opportunity ever to create economic value. All of us, I don't think there's a better time ever in this industry than where we're at today. And I deeply believe there's never a better time to be at Applied Materials than today. The opportunities are really tremendous. But we have to accelerate innovation. There's a 1,000x gap in performance per watt cost to enable the innovations needed for AI, big data, trillions of dollars of economic value. So what are we doing within Applied Materials? We're continuing to invest, and we will continue to expand these investments. Our Made in Technology Center, where we can combine all of these processes beyond unit processes to enable structures. We have those unique capabilities. We are accelerating those capabilities. We're accelerating how we work from an efficiency standpoint, from a productivity standpoint. We're accelerating all of that. We're using software. We're using sensors in new ways. We're using big data and machine learning in new ways. You'll see us expanding our innovation capacity so that we can accelerate these new structures by a factor of 3. Very, very important. And then also, fundamentally, connecting across the entire ecosystem. We're connecting inside Applied in fundamentally different ways, but connecting across the ecosystem, enabling the startups that are out there in the world today with new structures and new innovations. I guarantee you, we have capabilities in our labs that will enable structures, it'll enable devices in fundamentally new ways, and we are ready to connect with speed with the entire ecosystem. And I really, really think the opportunity for all of us has never been better. And I personally am committed, Applied Materials committed, to work together with all of you to make possible technology that shapes the future. Thank you very much.
And our next panel is going to explore this topic in detail, perhaps in a way that has probably never been done before. So I'm very pleased to introduce Dr. Ali Keshavarzi. He'll be the moderator of the panel and introducing the panelists. Ali is a well-known expert in the industry. He's had tenure at Intel, TSMC, Global Foundries. Most recently, he was Vice President of R&D at Cypress Semiconductor. He's currently a visiting scholar at Stanford University and is also a senior advisor and the industry liaison for DARPA's Electronic Resurgence Initiative. So please welcome to the stage Ali and his panel.
Good morning. I would like to welcome you to our panel discussion today. Basically, we have an exciting panel as we have put together an ensemble of experts, each covering a very interesting angle and a perspective regarding today's discussion panel. Glad to be here. So before I introduce the panel topic, let me introduce our panelists. First, Jason Wu. Jason Wu is a professor of electrical engineering at UCLA and also an IEEE fellow. He has worked on physics and modeling of the technology of devices, and currently his interest is on logic and memory devices for high-performance SoCs and also neuromorphic systems. He has also an eye on heterogeneous integration. Next, Chidi Chidambaran. Please, Chidi is a vice president of engineering at Qualcomm. He's leading the process technology and foundry engineering teams there. He has enabled Qualcomm to lead the fabless company and the industry, bringing leading-edge semiconductor technologies to manufacturing chips, particularly for mobile devices. Next, Jan Bardowski. Jan worked at Intel for 28 years and was a senior fellow at Intel when he retired in 2015. He worked on all aspects of lithography, led Intel lithography roadmap development, numerous lithography processes, tools, and materials. And he's been also involved in co-optimization of multiple nodes, from half a micron to all the way to 7 nanometer node. He has won IEEE Claudio Brunetti Award and also SPIE Fritz Zernecki Award. Mukesh Khare, please join us. Mukesh is a vice president of IBM Research, responsible for IBM's worldwide semiconductor research agenda, driving the logic and memory technologies. And he's researching ways to leverage materials and devices innovation to power the era of AI. Again, Mukesh has won several awards, and he's also a member of the board of directors of SRC. And finally, our final panelist is Steve Ganayem. Steve has been with Applied Materials for 28 years, and now is a senior VP of the New Markets and Alliance Group, focusing on applied, organic, and inorganic growth in new markets. He's also doing business and partnership, developing new business and partnership models. Steve, before his current job, he was the vice president of the Transistor and Interconnect Group and Applied, and has been responsible for many innovative products in a variety of the unit processes. So, welcome to the panel. Let me first, now let me just give you a quick background regarding the panel. First, let me talk about the environment that we are in. We are in a world where, on one hand, traditional driving engine of the semiconductor industry is slowing down. And on the other hand, artificial intelligence and Internet of Things applications are showing promising, tremendous new growth opportunities. And the driving forces and engines have been basically feature scaling and boosters, like both in 2D, like all the way down to the 3 nanometer technology node, and also in 3D. For example, effective scaling of the three-dimensional device like FinFET, 2.5D integration, 3D stacked DRAM, 3D stacked NAND, and even wafer size, all the way to the 12-inch wafer size, all lumped under Moore's Law theme. Now, augment that with von Neumann architecture, an architecture that has served our industry so well, basically connecting the processing unit to the memory via a bus. However, the power density, the energy, and the bandwidth of getting the data to the processing unit basically has been limiting us. And in the previous panel and all day, people are talking about they're constructing various walls, energy wall, power wall, a memory wall. So we're all familiar with that in the CPU domains, FPGAs, GPUs, and they're all used buses in one way or form. Now, this is happening, unfortunately, just when AI is coming to maturity, and AI requires this processing of huge amounts of data. It is relying on the things that are basically reaching their limits. What Gary talked earlier, the perfect storm. Before moving on, for the sake of just leveling, let's define the AI very quickly. the AI that we're talking about here is not really that general, the general AI or the science fiction AI. It's very specific. It's a narrow AI, something that, let's say, AI is about producing useful inference from data. Currently, most of the common form of AI uses machine learning methods based on neural networks, utilizing basically data flow architectures. We are familiar with GPUs doing deep learning, deep neural networks for a variety of applications. And what has driven that has been the computing performance and also the large data sets available to us. Basically, this has allowed us to do things like training, model development, and inference. Now, this machine learning is a method of achieving AI, that narrow definition that I had, basically by using algorithms to parse data, to learn from it, and then make a determination or predict something about the world. An important capability, indeed. It's very, very important. However, there are many uses of AI. Examples are wider use of linear algebra on dense and sparse data, graphs, analytics, scientific, and a wide range of optimization problems. AI has been mainly limited to the cloud because the limitations we are facing is based on required power, performance, and access to large data. Now, pause for a second and imagine if you can unleash the AI method into IoT applications, where the data is. What I refer to this as where AI meets IoT. In this domain, I call that edge intelligence, which, if you will, there is a multiplication factor going on here. It's both all the AI that everybody's been talking about, multiply this thing by the number of the IoT applications and devices, and the opportunity will be huge, particularly the growth opportunity. So, however, this panel is about what we need to make this reality, make it a reality, going after all kinds of efficiencies in this front. So, panelists, I have 3 questions, high-level questions to set the theme for the panel, and then specifically I will be asking you guys questions. So one is, with that explanation that I had, is what new architectures are needed for AI? For example, non-Neumann architectures. And then, should we consider brain-inspired architectures, like neuromorphic architectures, analog computing, in-memory processing, a quest for utmost efficiency measured by operations per watt metric, trying to reach the energy efficiency of human brain? And the third question is, what do these new architectures actually ask from low-power design techniques that we are all accustomed to, from new energy-efficient devices that they may be required, and unit process technologies, and also new materials that we may have to inject? So with that, I want to bring you back to the focus of the panel, which is innovative breakthroughs and collaborations needed from materials all the way to the efficient systems for the age of AI. So let's go ahead and start the panel, if we may. Mukesh, my first question is for you. IBM just made fastest supercomputer. How can we bring the capabilities to the chip level at the edge? That's very challenging. So, and the follow-up would be, where are we today? What innovations are needed? And cloud versus edge. But how can we have it on a chip?
Well, first of all, Ali, thanks for inviting me for this great panel. I will say this is the most exciting time for us to be in semiconductor industry. We are going through a exponential. And anytime we go through such exponential, which is the AI exponential, we have an opportunity to innovate and disrupt. So this is wonderful time for us to go innovate and create another $2 trillion opportunity. I'll keep going on the number ahead of that. So that said, yes, we did announce, IBM announced we built the world's most powerful supercomputer for AI. That's as John Kelly called earlier today, it's the Formula One. It shows what can be accomplished. But the problem with that, yes, it can do a lot of things, but the problem is that it takes 13 megawatt of power. And that clearly tells us that there is a significant opportunity to now come up with new material innovation, architecture innovation, algorithm innovation to take power down from 13 megawatt to where our brain is maybe not all the way, which operates at 20 watt. So we have an opportunity for several orders of magnitude improvement. In my view, or in our view, there are several parts to that. One is that in this AI era, to really disrupt industry, we need to look at end-to-end solution. The reason AI has come together or has become so important to business is because now data, algorithm, and high-performance compute are all together. So how do we design this system which are really optimized for end-to-end optimization? Now, for this audience, going a little bit more into the compute side, we believe that there are innovative ideas in the pipeline that can actually generate 10,000 times reduction in power in next 10 years. That's the kind of innovation that is required. And that's not traditional, let's call it Moore's law or slowing down of Moore's law. This will come with new architecture improvement, things like low precision compute, innovations in heterogeneous integration, which is very important. How do you provide the memory, the bandwidth required for this compute? And then the third one is fundamental innovation in the way we do compute the device, the material innovation. So I think these three in that order will provide us the path from where we are today, where the supercomputer costs 13 megawatt, to where our brain is, which costs 20 watt. So it's truly an exciting time. And I believe if we stay focused and we become the disruptor rather than being disrupted, then we can go on that journey together.
Okay. Thanks for your answer. Jan, you're next.
Okay.
If you think that the new architectures add value, then how do these new architectures enable unit processes? Any hope for achieving cost and defect levels required for high-volume manufacturing? And are non-von Neumann architectures more defect tolerant in principle?
Yeah. First of all, I agree. It's really a wonderful time. It's especially a wonderful time for me. I'm retired. So I am more of observer than participant. But I will comment on the question yet. I think there is a very deep connection between von Neumann architecture and Moore's law. And it's interesting that von Neumann, when he was starting his machines, recognized that reliability wasn't so good. So he actually was interested to find out, can he also come up with some kind of error correction for logic circuits to fix the problem? And his conclusion, he actually wrote a paper about it, that you cannot really save the problem with error correction code for logic function on logic gates. He kind of said, no, not going to be happening. So we know we can do it in SRAM, but not really on logic functions. Gordon Moore, in his foundational paper in 1964, also wrote that as feature size of transistor will become smaller, you can cram more of them on a square millimeter. But as you keep cramming more and more and more in square millimeter, defects will rise and yield will go down. So there is kind of natural limit to those. So both of them recognize there are defectivity limits to the von Neumann machines as well as ability to produce them. But industry as a whole over the last 60 years were extremely capable of dealing with defectivity issues. And I think as those two things were progressing together, both von Neumann machines, going to GPUs, to multi-thread, I mean, there is many, many things within von Neumann development. And just as Moore's law was progressing through all of the scaling in its tremendous space, I think they're both coming to the limits that something beyond von Neumann will also be held by beyond Moore. And this is what I mean. Beyond von Neumann to me means some level of neuromorphic computing. People who doing that, from what I have read, understand all the material issues involved in compute and memory and this kind of thing. And I think this is where industry can really develop materials that have better characteristics than now. They're more linear and so on. It appears to be that memristor crossbars is one of the fundamental parts of future neuromorphic computing. And if you take a look on this crossbar thing from point of view of processing, there is a material issue because those parts, depending what they are, either PCM-based or those are dioxide-based. There is many varieties of those things. They're incredibly defect-tolerant. Fundamentally, when you do training and then inference, level of defectivity of 10%, according to many published papers, appears to be sufficient to reach 98% accuracy. Some people quote that for their system, even 40% defectivity can get 97% accuracy. And you don't need 32-bit computing. You can do with 8. Yep. And 8 is just 64 level available in the PCM. Now, if you take a look at dimension of memristor, there is an article published months ago done in the University of Massachusetts, I believe, with people who are now still there, and I think part of them went to HP, where crossbar dimension is 2 by 2 nanometers on a pitch of 11.5 nanometers. And by the way, it's done without any expensive lithography. It's a sidewall deposition kind of thing. So it's, to me, when you can do something very dense on this level, 11 nanometer pitch or 2 by 2 nanometer feature, and you can do it with high level of defectivity, it equals to cheap. And I think as soon as this cheapness will actually be commercialized, a number of applications that I can do on the edge, as people say that, or laptop or whatever, without being tethered to cloud for training, will produce some kind of unexpected explosion of applications, just like with any other fundamental thing that is available to you personally. People will come up with hundreds of different ways to train their devices on whatever the way they want to train it. So I think if Moore's law was always about cost and number of transistors per square millimeter, I think beyond Moore, there always will be part for Neumann as a control circuit. But I think part which does training and inference and so on, there will be something beyond which probably will be based on number of neurons or synaptic connection that you can put on a millimeter square and complexity of synaptic connection beyond that. And so I think this will be something behind Moore's law, and next 3-4 generations of this neuromorphic stuff will allow us to define rate of change for those parts. To give you an example of tolerances, as I said, it seems to be 1 or 10% of defectivity for neuromorphic parts is okay to get reasonably good accuracy. For traditional lithography at this time, defectivity for, let's say, 7 nanometer should be better than 1 per 10 to the 12th. And the reason is, let's say, vias are not really redundant on current von Neumann machines. Any one of them being closed or not open will kill the part. And so if you have 5 sigma process, which is 1 defect for 5 million, you will have 20,000 closed or non-open vias. You're never going to get a working part. So we need, I think, there is a synergy between those two, and they need to switch.
That's perfect. Thanks for. We may come back at the end if you have time.
Whatever you say.
So Chidi, you're next on the question. What is going on at the forefront of the edge and mobile devices? Why inference at edge? At what power level? Is it 1 watt, less than 1 watt? What capabilities are needed? And what low power design styles for your SoC chips you're using today, and how you're going to change it tomorrow to domain specifics, I don't know, processing elements, what have you. And please let.
Yeah, thanks, Ali, and thanks for inviting me. So at Qualcomm, we are extremely interested in giving the handheld device the AI capability. And that's really, people talk about the exponential explosion and growth. And most of that has to happen where the users are. And that's really when you would see the user experience come true and the volume of AI actually manifest. You can look at it from a compute, like when you went from a PC to a mobile, you can see the scale of the entire industry reached a next dimension. So the same thing has to happen for AI. And today, what is the user experience of AI that's impacting people? It's things like, when you go to Amazon, it already knows what kind of things you like to buy or what kind of movies you like to watch. Most of this is relying on a cloud-based inference and training. But the future and the real scale is going to happen when you actually can deliver on your phone the true AI experience. So if a phone becomes your true assistant, then you can actually have it help you a lot more. So what kind of an application would something be? Like, if you're a bird watcher and you got your phone sitting, walking, going wherever you're going, and it hears the sound of that specific bird that you've been looking for, it wakes up and alerts you. That kind of application needs a standby mode inference that has to be implemented. And no amount of watt is, any amount of watt is actually high, right? Nobody wants a cell phone that's going to be needing to be charged more than once a day. You can't even make a commercial part and sell it to a user if you have to charge the phone more than once a day. So how can I make my phone that is in a standby mode do a lot of things, facial recognition, audio recognition, and things like that, and location recognition. So for that, you have to have the power consumption has to be less than a watt. You have to be really implementing things in a very, very efficient way. And today, Qualcomm has a lot of effort in that area, and we are making progress, but it's going to take a little bit of time to get there. Is the existing architecture sufficient? If you look at Qualcomm uses graphics chips and DSPs, and most of our AI engines are implemented using those architectures already. You can get SDKs and write web development codes using those. In the future, we will have a separate NPU, which is a neural processing unit that has architecture. But if you look at the GFLOPS per watt, they are all still incremental. For the very long term, clearly, I think people talked about the analog computing and in-memory computing already. Those have phenomenal power-saving value. If you can put a resistor and multiply the weight based on what the resistance value is and read the current out, you can get very, very low powers. But how far is that implementation based on what technology is available today? I think it's still 4 or 5 years out. And the main problem is not just the hardware, it's also the training and the architecture and the ecosystem is based on training for the cloud. They are so used to so many layers. ResNet has 50 layers, and it needs so much memory, and the precisions are all over 32 bits. So that ecosystem has to change down to something like a 8-bit precision and using lower number of nodes and keeping power as a key focus. I think when these two converge, you'll see a lot of adoption at the edge, and that's really what's needed before the industry can explode.
Great, thanks. Professor Wu, next question is for you. What critical research are being driven by this whole AI engine? Any promising academic body of work? What do you see the roles of the leading edge, half nodes, what have you, differentiations that they may be needed? So please go ahead. And any hope of, not a hope, any new materials on site?
Well, thank you very much for having me on the panel. I guess I'm the only university guy so far. And actually, it's a very exciting time for universities in addition to for companies. In the last 10 or 15 years, most university research basically just trying to make transistors smaller and help develop new architecture, nanowire, really focusing on how to propel the digital scaling, Moore's law. So with the AI advance. So now we have a new bunch of students trained on thinking devices very differently. And as all mentioned by previous panels, power, of course, has always been very important for scale devices, but it's now become even more critical for driving AIs. So many of the research in the past looking at things such as new device mechanisms or new materials that allow you to go to much lower power, let's say switching, things such as NC FET or tunnel FETs, now has breath on a new life to looking at completely differently. Apart from the requirements are different. For example, for tunnel FET, used to be one of the key concern is variability. But if you don't need that kind of precision, but really for a lot of AI applications, we can think differently. The other thing is really on the minimization of parasitics. In the past, for logic devices, if you have in-love on current or small enough off current, you can actually tolerate probably much higher parasitic. So the whole device design concepts, looking at how it minimizes the overall power, take on a complete new meaning. And the same go for memory, especially for these 2D memories. There's a lot of work going on in the past on PRAM, MRAM, or resistive RAM, really thinking of a replacement for NAND. But now, with this crossbar architectures, it actually come in a completely new life. And we need to look at completely new, different material, or at least advanced material, so that we are talking about more linear programming, scaling, analog, memristor. And at that end, maybe we can even think further, because one of the things that's been discussed for Neumann, one of the key power consumption is actually fetching the data and then putting the data back into the data bank. Either you have 3D stack, high memory bank, but it still takes a lot of energy to swap those data out. So localizing the data, distributed memory in together with devices would be one thing that universities should look at very carefully from both architecture point of view and the device perspective. So packaging and 3D, including chip-on-chip packaging, is one thing that we've been looking at very, very intently, allowing basically have a substrate, which is also a silicon substrate that allow you to have a lot more fine pitch in the connections, and you can actually then distribute the compute element with the memory element on the package level. And you can also, together with 3D, we believe is one of the major power-saving way to do that. And that's also allow university to actually have a lot of innovation in material science, in processing, and in developing new architecture. Now, go one step beyond, of course, is the analog computing that we are all talking about, or going into neuromorphic type computing, where you actually can combine memory and the logic into one single device. Now, Crosspoint is actually a prototype of it, but it's a two-terminal device, and hence you always have IR drop across and across each element. So there is a finite limit how big you can actually scale it up before you actually need to boost up the signal or the power. So one thing that we've been looking at, and a lot of people are, can you actually build equivalent type of analog memory, but as a three-terminal device with built-in gain? So one of the things that start with IBM and later on GlobalFoundries, now UCLA working with them on such as charge trap memories, would be one option that actually would have a transistor-like device with built-in weight function inside. So I think the opportunities are plenty, and in one addition is then the students all need to go back and learn quantum mechanics, because many of these new mechanisms now is no longer the traditional classical physics, but we need a lot more sophisticated physics, not only algorithm, but physics.
Thank you.
And beyond just like qubit and things. And I think it's an exciting time for students.
We will all come back as your postdocs. Thank you very much. So Steve, the questions for you is, we heard from all the panelists, so what do we need to go from this wide range, including the participant of the panelists? We go from all the way from materials to devices to architectures to systems. How can we address this huge task, and how can we co-optimize across the board?
Well, I think You know, at Applied Materials, typically we've done a lot of materials innovation, as Gary talked about earlier, and we have tended to operate under the radar of, you know, the big customers, Intel's, TSMC's, IBM's, et cetera, where they've done the wafer fabrication. But a lot of that has been kind of built on the back of materials development. So I think, you know, materials, we talk about materials-enabled scaling, which we think has been going on for at least a decade or so. You know, if you think about SiGe channels, high-K metal gate, these were materials-enabled technologies that really drove performance. But with all these changes coming, we see that there will be an acceleration of the needs of materials enablement, whether you're married to a PC RAM or a ReRAM, all of these different memories, all of them require very intricate materials engineering development going forward. So we think we're not married to any one of these technologies. What we want to do is enable multiple winning technologies through our technologies. And we think one way to do that is to have a better, I'd say, co-design and collaboration across the industry. The times when you just jumped on the node train every, you know, from 22 nanometer to 14 nanometer to 7 nanometer, 10 nanometer, whatever, you can just jump on and use the design ecosystem to generate something. We think that that's kind of coming to an end, where we think there needs to be greater collaboration between the materials guys like us through the device development, all the way up the chain, hardware, software, and systems. And if you look at a company like IBM, for example, that operates all the way from, you know, hardcore research all the way to the top of the stack, they really understand the requirements from the top. And basically, we think that those requirements are going to drive the right activity down at the bottom. And so what we need to do is being able to bring those things closer together so that we can move faster as an industry. If we do it serially, it will never get done. So really this kind of idea of co-design, co-optimization, more alliances and collaboration across the whole ecosystem.
Yeah, actually I cannot agree more with you, Steve. You kind of come back the full circle looking at end-to-end optimization. And I also second what you're saying, that materials innovation will be the real driver here. And yes, people still think that a lot of AI is software. AI is not software. AI will be optimized across the entire stack. And truly, you know, some of the innovation in material and creating these new devices will really drive the type of power reduction that are required to go from a 13 megawatt supercomputer to a 1 watt that Chidi is asking for right now.
We are asking for microwatts. Steve, I wanted to ask a follow-up regarding what you were just talking about. Do you really see a bifurcation in the technology needs of leading edge? Because in the previous panel, some of these startup companies are using relatively mature, advanced nodes, but mature. So is it really requirements are?
Well, I'd say what we've seen over the last few years is just as we supply our equipment is that, you know, a lot of our revenue has become bifurcated. There's a lot of revenue. We're shipping a lot of tools for 28 nanometer, for example, and the number of wafer starts on the leading edge has really gone down over the years, considerably lower and lower. The peak production of the leading edge has dropped over a number of nodes. So we see that bifurcation, but that doesn't mean that people won't still drive the leading edge. And we think from a materials engineering standpoint, Applied can still add significant value and drive forward on leading edge technology. People are trying to you know, solve these memory wall problems. So there's a lot of materials innovation in packaging that we can enable as well. But what I see is that, you know, these things will be the normal business and they'll go forward. There'll be a lot of work on packaging. But in order to enable these new devices, all of these kind of in-memory compute, it's gonna require a different level of cooperation in the industry. And, you know, from my point of view, who better to solve those materials engineering problems than Applied Materials in cooperation with many of our partners?
Yeah, if you look at the power it takes, the inference does not necessarily have to be on the leading edge, right? If you think about, like in the standby mode, I want to do something, the time is not super critical, but the ability to compute and access all the information in a very low power is more important. So I think it'll drive multiple technologies all at the same time.
So you have given up doing on some kind of a learning at the edge next to the data?
No, I think the edge learning is also going to be important. I mean, ultimately, the user doesn't want some information. Security, for example, right? Privacy and security is key, and the people at the phone user doesn't want to be trained on all the data they have, right? There has to be some control with the user on what data is going to be sent to the cloud for training. So there will be some amount of very small, optimal, personalized training that happens, but it probably doesn't need to be the one that's in the cloud, which is going to have a much larger data set and a big data problem.
Yeah. Ali, before we close, one thing
I'm not going to close, but I was going to come.
One point I wanted to make is that although we are technologists here, but we are developing a technology which will impact human lives. And I want to make sure that we, as a part of this, we have a pretty big effort at IBM to study the ethics of AI. How are you going to apply AI? And that's an area that this community also need to participate. Because at the end, the way we think of applying AI and people who are developing AI, are we creating, for instance, if I look at this audience, there is a very low diversity, gender diversity in this audience. And I think it's very important that we, as the leaders in this process of developing AI, are also making sure that the right set of people who are participating in developing technology so that the technology can be used by the entire society. So that's very
Although at the very beginning, I narrowed the scope. I said, we're not talking about general AI, and we were talking about something very specific. In fact, that's why even with the neural networks, like just say, we don't have to necessarily be a deep neural network. We can be some shallower version.
That's right.
For the sake of, this topic is very dear to all of us. We are probably going to go back and work on this thing, including many people in the audience, so we can talk forever. For the sake of time, as time is coming up, please allow me, I had second round and third round of questions, but for the sake of time, we need to wrap up. So please allow me to close by. Let's thank the panelists first. In a very high level, really, this exciting panel was, in fact, a call for leadership. In fact, initiated these discussions. Facing a promising future, but with many challenges ahead for AI and our industry. This, to me, really has translated this call for leadership, after listening to this panel, to a call for action. We really got to go get to work. We need innovations and co-optimizations all the way from materials to processes, to devices, to architecture, systems, algorithms, the whole thing. And we need to be able to do it cost-effectively, as Jan was mentioning earlier, and perhaps through new architectures, more malleable architectures, post-von Neumann, more inspired by our brain, in order to go ahead and try to tame this storm that is coming toward us, hopefully for something that it will be, as Mukesh calls it, an AI exponential. Thank you very much again. So let's thank the audience and the panelists one more time.
Thank you. It was great.
Thank you.
Good.
Thank you. Well, thank you, everyone. If the panel gave us some food for thought, we now have food for you. So it is lunchtime. We have boxed lunches for everyone. It's in the forum, which is kind of out the theater and across the way. People will guide you. Pick up a boxed lunch. You can come back here. It's a beautiful day in San Francisco if you want to be on the plaza, wherever you'd like to have your lunch, but we will begin again at 1 p.m., so please be back for that. Thank you.
Thank you for being here this week. We're collectively taking the industry into exciting new territories. To discuss where we've come from and what the road ahead might look like for new devices that will drive us beyond smart, we'll turn to the latest co-recipient of the Turing Award, Dr. David Patterson. It's my great pleasure to introduce our next session. The Turing Award is an annual prize given by the Association for Computing Machinery, and it's generally considered to be the Nobel Prize of computing. The first award was given in 1966, and the most recent award is our special topic today. We're here to pay tribute to David Patterson and John Hennessy. David is a distinguished engineer at Google, and he spent most of his academic career at UC Berkeley. John is the chairman of Alphabet and spent most of his academic career at Stanford. Together, as you saw earlier in Gary's presentation, they co-authored a textbook on computer architecture that has educated generations of the world's leading computer designers. The latest Turing Award recognizes their joint work on the RISC architecture, which revolutes microprocessor design and is now found in billions of chips shipped every year. The smartphone in your pocket is based on one. The very latest edition of their book adds a new section about designing for AI. Notice this list of Turing Award winners. They all have something in common. Each one was awarded for contributions in AI. You'll notice the awards go all the way back to the beginning of the industry. Author John Markoff chronicled this history in his recent book, Machines of Loving Grace. Please welcome to the stage Turing Award winner Dr. David Patterson, author John Markoff, and University of Wisconsin professor Mark Hill. Thank you. David, it's a pleasure to meet you.
Afternoon, everybody. I'm John Markoff. This is Dave. This is Mark. And we're here to honor Dave's prize and talk about Dave as a teacher. But before we started, just a personal note. Dave was tremendously significant in my career as well. I think it was more than 35 years ago as a young technology writer. Dave sort of took me under his arm and introduced me to RISC. I was working for Byte Magazine, and he sent me down to Stanford, and I spent maybe 3 weeks at the Stanford Library trying to understand computer architecture as a layman. And I read Manolis Katavanis' dissertation on RISC and wrote the first technical article for Byte Magazine on RISC. But first things first, France or Belgium? Dave?
I was rooting for Belgium, but France is a very good team.
It was a good game, yeah. And how about if you had to pick between France and England and Croatia, who would you?
I think I would like to recreate what the Battle of the English Channel and see France versus England. And France has won it recently, so England's been suffering since 1966, I think. So I think they're the team I'd root for.
Yeah. Mark, are you into soccer at all?
Absolutely.
So do you have
I missed this semifinal, but I'll watch the replay.
Yeah, it was pretty good. It was exciting. So the Turing Award is kind of the Nobel Prize for computer scientists. Has winning it changed your life?
I'm surprised. I've been fortunate to pick up a couple of awards along the way, but this seems to be a different kind of award. I get people who don't know who I am or what I do invite me to give talks based on the fact that I've won the award. And I'm kind of the same person I was about 3 months ago, but now this award puts me into some rarefied category where people think anything I say must be important because I got this award.
You have this tradition. I've seen a couple of these talks that you give. I think of it as your Bad Career series.
Yeah.
And so by way of your bad career, I wanted to ask actually each of you sort of how you came to computer science. What brought you to computer science, Dave, first?
Yeah, so I grew up in Southern California. I went to South Torrance High School. They didn't really normally teach calculus at the time, but I got placed in an advanced math class, and it was calculus. And since I loved my math teacher, and so he said he wanted to be an actuary, so people asked me what I do, I'd say an actuary, even though I didn't know what an actuary was. And I went to UCLA, and then in the last quarter of my junior year, a math class was canceled, so I had to fill up my schedule, so there was a half class in computer programming. And so I took that. I knew what computers were, but no one ever told me to go study them or stuff, so I took it. But then I was hooked, like a lot of people.
Was it Fortran or
was it Fortran on punch cards? But there's still that excitement of being able to see the idea, feel your ideas come alive in the computer, right? And that I was hooked. There was no computer science major then, but my senior year, I took all the engineering and business classes in computing, like, I don't know, 9 out of 11 classes, and then I did well in one class, and one of the young faculty there at UCLA generously asked me if I wanted to get involved with research instead of working, in a factory to support myself going to school, and so that led me to go to grad school, and that's how I got into it.
And Mark, what brought you to computer science?
Well, so I was always a logical person, and I did, as an 8th grade science fair project, I did a mechanical binary adder, which I thought was pretty simple. But apparently the judges thought it was pretty good, because I did it completely by myself with no parental help. And so I went up.
What did you build it out of?
There was wooden blocks, and the zeros and ones came from address things you put on your house.
Right.
And the carry, actually, the arm came down to do the carry. So I fell in love with computers, and partially because everyone was telling me what to do, and when I told a computer what to do, it did exactly what I told it, even if I told it the wrong thing. And I thought that was completely fair. I was also the first, I went to the University of Michigan. I was the first person from my family to get a bachelor's degree, and I fell in love with school so much that I just never stopped. Got a PhD and then spent the next 30 years at the University of Wisconsin.
Boy,
PhD with David Patterson, I might add.
He's one of my proud descendants.
So neither of you had science or engineering in your family? Were you both sort of first?
Right.
Isn't that
I'm like Mark. I'm the first of my family to get a college degree. And my mom said that when my first week in college, she said, I came back and said, I could do this forever. And little did she know that's what I was going to end up doing.
But, I mean, you guys are unusual, actually. I can't tell you how many people I run into in Silicon Valley who are failed physicists who have sort of fallen into computer science from physics, right? Isn't that?
I know Butler Lampson's like that.
Yeah, there's.
No, I don't feel any inferiority complexes, which some of people of my generation do in computing. We're not physicists. Hey, we invent the technology that changes the world. I'm not embarrassed about being.
My mother was a bookkeeper, and my father would climb in and do maintenance on industrial scale heating and air conditioning machines. So there was a logic in the family, but not the education. And I guess if it was going to be something else, I would have been a mathematician. But as a lower middle class boy growing up, people told me as a mathematician you can't make any money.
Yeah, that's why I was going to be an actuary.
And in my case, that's probably right, because I think I'm a way better computer scientist than I would have been a mathematician.
But Dave, you came to academics you started in aerospace. I'm surprised you didn't, was there a chance you could have stuck in aerospace for your entire career? That would have been a very different.
Yeah, you've heard my story, but I'm married to my high school sweetheart, and we've been married 50 years. But so I had no plans to go to grad school, but this person got me in. My senior year, I started working as an undergraduate, and then I could get into grad school for a master's degree, which seemed cost-effective. And then I asked my wife if I could keep going, because everybody else in my office was getting a PhD. So I thought, well, that seemed like a good idea, and she was okay with that. Let's see. So the question was, how did I get into academics?
Well, you ended up in aerospace first, yeah. So.
Yes. Well, I lost my job. I was supporting a wife and 2 kids in a 20-hour-a-week RA, and that RA ship ended, and so I had to get a job to support the family, and so I started working for Hughes Aircraft, which was an aerospace company at the time, and I had done mostly software, but they needed somebody in hardware, so I did hardware. We designed computers, airborne computers for Hughes, and I was there for almost 5 years while I was trying to finish as a grad student. And if my wife, who, we lived in married student housing and didn't have much money, and my younger sister and her younger sister both bought a house and had a brand new car, and we were still poor. And so when it came time to graduate, I'd make a lot more money if I stayed at Hughes, but we had an offer from Berkeley, and so my wife asked me 2 questions. The first question was, if we go to Hughes, can we later go back to Berkeley? And nope, we can't do that. If we go to Berkeley, could we later go back to Hughes? And I said, yep. And so she said, okay, we'll be poor but proud. And we went to academia. And I still haven't Still haven't gone to Hughes.
Mark, what brought you to Berkeley?
So when I graduated from Michigan, I looked at the best graduate schools around, and I think it was the combination of the computer science strength and the sort of atmosphere at Berkeley, giving away my politics a little bit, that attracted me there. Now, I didn't marry my high school sweetheart. I, in fact, was a teaching assistant who signed off on this young woman's project, which meant that she graduated from the class, which meant she got her bachelor's degree, which meant she got into library school. And so she chatted me up, and then after the class, we went out.
He
Subsequently got married for 30 years.
Yeah. He keeps saying it was after the class, and I have no evidence to the contrary.
So how did you come to be Dave's student?
So I was looking around at a number of professors, and I remember approaching Dave, and he gave me a test. You probably don't even remember the test.
No.
The test was to do some decimal arithmetic routines with the RISC-1 instruction set, because I guess you were getting some criticism that RISC couldn't handle commercial things.
Okay.
And I apparently passed the test. But what I saw in Dave was somebody who wasn't just going to give you technical advice, but he was going to sort of grow the whole person, kind of like a great sports coach, and that was very appealing to me.
And was it your relationship as a student to a professor, was it kind of a one-on-one mentor to tutor, or was it more like, was there a RISC team of graduate students that were on the project all the way through that you joined?
Well, there's a team, but there's also a relationship. I mean, it's really a master-apprentice or almost a parent-to-child relationship, and it's very strong. It's the last vestige of the master-apprentice method of teaching. It's very time-consuming, but we haven't figured out a textbook way to teach people how to do research, and you have to do it by example with a master.
Yeah. And you, I mean, as a student, you worked on one or two or three of the follow-on RISC chips, and so you sort of were tutored to become an architect. Was that the way you described the apprenticeship?
Right. I actually went to Berkeley to be in operating systems, but became more fascinated with architecture. I tended to like the things where you were doing things that were impossible. So a lot of my work was on caches, and caches create the illusion of a memory that is faster and cheaper than any technology can individually do, and that always appealed to me.
And so if you jump from the early 1980s when you were a student to today, how much of the tools changed? Did you work by hand in the early 80s? Do you have more sophisticated tools now? I'm asking this kind of as an augmentation question.
Yeah, the tools have fundamentally changed. I remember we visited a company at the time, and they were even laying out their chips by cutting Rubylith, right? And now it's just, when people say, by the way, there's a software crisis, we can't write software, we can't design hardware, we could have no trouble designing the software and hardware of that day. Our just ambitions keep going up, and the only way we have any prayer of doing it is the rapid tool changes. And Berkeley is pioneering some more with Chisel and things like that.
You created a group called the AMP Lab later on, David. Were there any projects in the AMP Lab that were sort of better tools for architects to do design work?
No, not so much that. Probably the biggest success was a system called Spark, which is kind of a computing environment for the cloud.
Oh, this is not Spark of Sun era.
No, this is Spark with a K. It's got, there's startup companies and, it's got its own conferences and stuff like that. But it's kind of, think of it maybe as a successor to MapReduce, maybe. Yeah. It's easier to use thousands of computers, and typically for using machine learning. But there wasn't the tie-in for computer architecture for that.
What are the roots of your original RISC work? Why did you start the RISC project?
I took a sabbatical as an assistant professor in Boston at a company that was called Digital Equipment Corporation, which was the leading mini computer manufacturer at the time. What had happened, the way we were building computers in the 1960s and I guess 70s was that you'd have these instruction sets, and the way you did control is you wrote an interpreter in what was called microcode. So a little read-only memory that have the control, specify the control, and you'd write these little interpreters in that. And what happened due to Moore's law is the control memory was able to get bigger, so the instruction sets got more complicated. I was invited on my sabbatical to help them with the bugs that were in the microcode because they got more ambitious, and it took a while for bugs to get out of it. And when I came back from sabbatical, I wrote an article that said if we were going to build microprocessors with more complicated instruction sets, so that there'd be bugs in the microcode and we'd have to repair them in the field, and that paper was rejected. And so I had in my mind that the microprocessors of the future, they're copying what the big computers do to make instruction sets more complicated, and it's going to be but that's a bad way to design microprocessors. So that was kind of like, all right, we need to do something different. And then I started a sequence of graduate courses where we investigated the ideas and ultimately built chips over 4 quarters at Berkeley.
And how many transistors were involved in a RISC-V microprocessor?
I don't know exactly, but it's around 44,000. And we didn't cut Rubylith. Fortunately, I had friends like John Osterhout who built CAD tools at the time, and if there'd been Rubylith, the students would still be there, I think.
But students would have been out of there.
Yeah, that's true. We never would have finished.
The RISC idea caught on at Stanford too. How did Hennessy and his crowd start down a RISC path? Was that independent or?
No, we were both funded by DARPA and in the VLSI program, and so he was aware of what we were doing. So we did a graduate class to investigate the ideas, and John did too a little bit later. But just like, from first principles, what's the right thing for microprocessors? We shouldn't just imitate DEC and IBM. And both of our groups decided something much simpler would be a way to go. We joined forces because we could have been Stanford versus Berkeley. Those guys are the enemies. But it made sense to both John and I that look, everybody else was the enemy. We needed to find allies that would argue the same side of the argument. So we were kind of friendly rivals, but supportive to each other.
I have to say that was part of my education. I remember in my first or second year, you invited what I thought was the enemy, Stanford, over to a meeting at Berkeley, and it made me realize that you have to take a bigger perspective on who you're sort of friendly competing with and who you're having a more adversarial relationship with.
Yeah, I mean, that would have been, if we had done kind of the classic academic thing of go head to head, that wouldn't have been good. That would have made it harder for it to be accepted.
And I think another thing is about our field is that ultimately influence is determined by industry adopting things, which is a combination of technology and business. And unlike a field, let's say you're arguing interpretations of Shakespeare where you argue, and here the two groups could realize that there's a bigger group to influence than to figure out whose papers got more citations.
You took the ideas to industry in different ways. Hennessy went to MIPS or became was one of the founders of MIPS. You took the ideas to Sun, but you didn't do a startup. Philosophically,
I think I had some time. I got the job offer from Berkeley it was pretty late in the season, like July, but I didn't finish my dissertation until December, so I had time to think about things. And how was I going to be academics? And for some reason, I read this book that at the time that was called Working by Studs Terkel, where he interviewed people in their careers and they look back and see were they happy with their careers or not. And what I got out of that book was, people who built things that lasted forever, like the Empire State Building, Golden Gate Bridge, they felt good about it. The stuff was still there. And people who worked with people, like priests or teachers, felt good. So I thought, okay, well, I'm going to go teaching, and the payoff's going to be the people. And so I was kind of, I was kind of an idealist or something. It's like, well, I got to stay in academia to create students like Mark, and that'll be my legacy, and I got to do that. And I didn't. And when I was asked in the RISC era, did you want to start a company? I gave my little speech, and they said, okay. and so I stayed at Berkeley and never tried to start up for 40 years. I think I was just I was too too dedicated to the idea of the importance of academia. It would have been okay for me to take a leave for 2 years and done it, but, so I didn't do it. But this tradition at Stanford, particularly then, was to start companies, and so it was a natural thing for John to do. My involvement was another company, startup company that had Berkeley people, particularly this guy Bill Joy, who was a real Renaissance person, hardware, software guy, and he believed in risk, and he thought this startup company could do their own instruction set. So he recruited me as a consultant, and that led to the Spark effort at Sun Microsystems.
So why did, so RISC ultimately took over the world, but it didn't on the desktop. Personal computer. So why do you think it was, there was a certain point that Andy Grove decided that I was a RISC bigot, because I was a bit of a RISC fan, and it was my one shouting match. It wasn't actually a shouting match with Andy. He shouted at me for quite a while about my RISC-related articles. But he did manage to hold the line against, why didn't RISC take over on the desktop?
Well, John and I I've spent a lot of time with John. He was president for Stanford for 16 years. So I would see him periodically, but since the award, we've been spending a lot of time talking together. I mean, he had there's a point that he made, had the RISC people agreed on a single instruction set. If we'd rallied around one instruction set, then that might have had a marketing, that might have had momentum behind it. But instead, there were all these different variations. And it turned out that binary compatibility was important, right? It wasn't so clear when the RISC stuff started. Everything's in high-level languages. You can just recompile and it should work. That's basically what we said. But binary compatibility, distributing software in this form was a better way to do it. And so that was more important than we expected. Had we agreed on instruction set, that mattered. And then basically, to Intel's credit, they figured out how to put design teams of 500 people, which other people couldn't, that would have maybe 50 or 100. But they could make 500 people work together, and then they would overcome the disadvantages of the x86 instruction set to, amazingly enough, translate in hardware from the x86 instructions into RISC instructions, and then any good RISC idea they could do. So, through great engineering, and they had much better technology. They could overcome the disadvantages of RISC, and then they had the volumes because of the PC market to be able to do that.
They also did branch prediction, which was so good that they could hide the latency of doing all that decoding. But I happen to remember on one of those chips, they called the decoder the volcano, because when you looked at a heat map of the chip, there was this little triangle feeding the processor.
Which finally caught up with them, right, at a certain point. Yeah. So, Mark, you decided to go into an academic career. Were you tempted at all to?
I was tempted by industry, but as I said, I went to the university and just fell in love with being at a university and the intellectual milieu. Now, Dave did teach me that you need to keep strong connections to industry in our field, because we're not a field of beauty only, and that if you're not relevant and you're not paying attention to the problems, you have difficulties. So I've long consulted, and in fact, I'm currently doing my third sabbatical in industry to make those connections. And one of the things people wonder is like, well, what's it in for the company and what's in it for me? Like, for the company, you have somebody throwing ideas, thinking differently, and maybe having good ideas. From my point of view, I can't take away any of the company's solutions because that's their intellectual property. But I have and I will take away problems that are just emerging, that are not being solved yet, that are just being band-aided, and then take them back to academia and then study them more deeply and grow some more great students.
So about 15 years ago, I had a conversation. Well, it must have been longer than that ago. It must have been 20 years ago. I had a conversation with John Hennessy while he was Dean of Engineering, where he was very proud of the fact that he'd figured out this model for cycling his faculty out into industry and then bringing them back. And I forget what the periodicity was, but he had a model. I just read this piece in the Times by Cade Metz about the stunning salaries that are being offered to
the machine learning people.
Yeah. It's just, and is there a danger of basically eating our seed corn, or how does it feel now in academia?
Yeah, I think that's a real worry. I remember a Stanford professor, and she was having a hard time paying her child support, and suddenly being offered the moon. I don't know how far the moon is, but I have the feeling it's millions of dollars, right? So I think a difference. It's always been more money in industry, but it's possible now it's a lot more money in industry. I don't know. Does your group
and we've
say
gone.
that?
I mean, as an industry, we've gone through different phases of this, where industry was looking better and the salaries were higher, and this machine learning phase sort of could be more extreme. I think in this case, universities maybe have to look for some greater flexibility, because they can say, I don't like this professor who's gone half the time, but plus 1/2 is better than 0.
Yeah, I talked to Hennessy about this, and he was president, right? And is it plausible that we could, in the future, have somebody who's half-time a professor at Stanford and half-time at a company? And he said that might be the way things are going to go. There's all the benefits of the problems he talked about. And faculty often consult 1 day a week now. So and if there's going to be, and then there's the arguments about access to data. The companies, because they're worried about privacy, they can give you access if you're an employee, but not if you're outside. And then access to machines. Millions of machines. So and then the financial stuff. So there's a possible evolution where we're going to have in the technological fields people who are half at a company and half at the universities. That's that's going to be a giant change, but that may be what we're facing.
I know at least one university and with one company where you can dial your percentage with the university that year. Yeah. Another big conundrum here is students, right? What you don't want is faculty consulting for a company and essentially using the student to help their consulting. That's totally inappropriate. But there are many situations where something similar to that is really good for the student. And it's just good to not have knee-jerk simple reactions, but have a lot of, some Supreme Court justice said that the best disinfectant is a little sunshine. I think as long as you keep the relationships in the open, it's good to be flexible.
Dave, we first met, I think, when you were, I was a little bit more about pedagogy and your teaching. I think you were trying to teach Smalltalk to undergraduates when we first met.
Probably, yeah.
I mean, how did your philosophy of teaching, did you continue to sort of focus on undergraduates or?
Oh, I think a question I'd get a lot is, oh, you're a faculty member at Berkeley. Do you teach undergraduates? It's like, of course, that's the job description. I mean, so my sisters, my sons, and myself all got degrees from the University of California. And so I'm just the believer in public universities, and big part of that job is the undergraduate piece of it. So I've always loved teaching, and there's the excitement of seeing young people, learn new ideas for the first time, which is very rewarding, as well as, working with tremendous graduate students and pushing the state of the frontier. So it's just like it's a perfect type of job for people like Mark and I.
I mean, teaching freshmen can be really fun. By the way, fall freshmen are not as strong as spring freshmen because they still might not do their homework without their mother looking over their shoulder. But there's a real special thing when you show somebody really and truly they get it, that the bits can be data or instructions. And there's concepts like that are fundamental to our field that are really early. And it's just fun to see the light bulbs go off. Or you can actually explain undecidability at some level to freshmen. And most of the class will say, who cares? But then there'll be 5 people that'll come to your desk, and at least one of them who came to my desk as a freshman is getting a PhD now. That's not a causal relationship. It's probably correlated, but it's satisfying.
So one of the things that was enjoyable about being a reporter and covering what you did is that you, over the course of your career, there were many places that you touched down in with new ideas. RISC, RAID, massively parallel computing were all places it was really fun to report about. Did you have ideas that didn't go anywhere?
Sure.
Do you have any favorites?
It's research. So
like register windows
well, that's a detail. But another example was the IRAM project. So this was it stood for Intelligent RAM, and the idea being that why are we going to have both a logic fab and a DRAM fab? Wouldn't it make sense at some time in the future to put the processor and the memory on the same chip, right? And that was Intelligent RAM. And so, it's a credible idea, and we built chips and demonstrated prototypes, and there are slides that are that are present, right? There's a slide that says, I think in the future with this technology, we could put all these devices, phones, calculators, cameras, garage door openers, all into a single device. And we'd have this one handheld thing, and it would have an IRAM chip in it. And, and that was, in 2000 or something like that. But that didn't catch on. The disadvantages of the speed of the logic in a DRAM technology and the density of these embedded DRAM technologies. So it didn't catch on. But it was a plausible thing to try to do, for some reason, I ended up on this model where we would do things for 5 years. So let's think about the future technological trends. You can imagine how the world would be different in 8 years. So let's do a 5-year project to try to make that happen. And so I did a bunch of 5-year projects, some of which were home runs and some of which were near misses.
And I think that one of the things to take out of this is one of the most important challenges in research, which Dave taught me, was that it's not always about the solutions, it's about picking the problems. Picking the problems is the hard part. You want a problem that if you can succeed, people will care, and you want a problem that permits progress, and possibly you have to break it down to permit progress. And if you do that well, solutions follow. And in the worst case, if the solutions don't end up being important, you've produced some great students who learned how to think.
Yeah. So now you're at Google. You're helping them with design issues. And
I'm part-time at Google and part-time at Berkeley, but yeah.
My sense is that, and tell me first if this is right, that in terms of architecture, we have tend to swung back and forth between general purpose computing and special purpose. And are we in that kind of a swing now? Is the TPU, their part that's optimized for machine learning, an example of that kind of a swing?
Yeah, I think, Mark and I representing computer architects, I think it's like, if you were to poll us, I think 95% of us say the future is special purpose architectures. It was a bad idea to go to multiple processors per chip because it'd be hard for software. We had no other choice with Dennard scaling in 2004 to go to multi-core. And we've run out of ideas now. Multi-cores run out. The only thing left is special purpose architecture, domain-specific architecture to go forward. And I think everybody believes this approximately. I don't know.
Well, and what's unfortunate about the word special purpose is some of these things are both special and ubiquitous, right? It's like everybody wants speech recognition, right? Everybody wants the machine learning apps. Everybody wants the signal processing. So it's special and ubiquitous. And it's an exciting time. And also, these things require crossing many layers from devices up, which in the 20th century we had the luxury of not doing. We could each work within our own layer. In fact, that's all we had time for because things were happening so fast.
So a couple of years ago, when the end of Moore's Law loomed, I spent a couple of days at the industry partners meeting at Stanford. And everybody was talking about hitting the Moore's Law wall. And I had dinner at the end with a young computer architect from Harvard, and he was ecstatic because basically he said, "Now it's our turn."
Yep.
Which is really a neat idea, but on the other hand, that's the Moore's Law was like turning a clock. You would come with you would get innovation at a regular pace. This innovation from creativity is kind of episodic.
Yeah, but even when you were turning the crank, there was a lot of perspiration to turn the crank, and there was a tremendous amount of innovation. If you just take the technology that these guys are experts on, this sort of, it seems from the outside, it's moving inevitably. There was a whole bunch of, really cool, specific, seemingly one-time innovations.
Yeah.
Yeah, we were turning more transistors into performance because people didn't really care about more transistors. They cared about performance. And that's what the layman thought Moore's Law was. I'm throwing my laptop away because my neighbor's laptop is 3 times as fast and I can't get my work done, right? That was that era. Mark said it just right. And so that's why Hennessy's and we give a lecture when we get the award. It's called A New Golden Age for Computer Architecture. It was like in the 1980s when we did our research, and Mark was a grad student, that was an exciting time in academia and in industry for computer architecture. We're saying this next decade will be the same thing. If we're going to have to change the architecture to make things faster or more energy efficient or more secure.
Are there any
And I think
ideas?
it's going to go even further down, right? I mean, we build everything, on these digital switches, these transistors that go 0 or 1, to get the tremendous energy efficiencies, as some of the previous speakers have talked about. We're going to have to revisit whether we want just digital, and especially for things like machine learning and neuromorphic aspects. You can do non-digital things, analog to low precision, and I think it opens up new possibilities. And I'm not a process technology expert, but I have a hard time believing that if you have to build a device that has to be accurate over a range, that requires much more innovation than doing a digital device.
The other aspect of sort of the stalling of Moore's Law, it wasn't just faster, but it was also cheaper, faster. And the falling cost thing, transistors are not falling in cost the way they did.
My friends who build things at TSMC says the cost per transistor is constant across technology nodes now. So that was the Intel excuse that Moore's Law was continuing. Well, Moore's Law maybe isn't going, but the transistors are getting cheaper. Now, at least at TSMC, the transistors cost the same no matter what technology node you're at for the last few nodes. And, I don't know what's going on inside of Intel, but they've announced publicly that the 10 nanometer thing has been delayed a couple of times. So I think this is what the end of Moore's Law looks like.
And they abandoned tick-tock, where they were alternating architecture changes with technology node changes.
Because I had this sense that, as we went down that curve, whole new industries would come out of, largely out of cost changes.
Well, yeah, I think Gordon Bell has some kind of saying is that every time you cut the cost in half, the market increased by a factor of 10 or some number like that. Yeah. And so with many doublings, then this is what happened, right? When I went to grad school, my relatives thought, well, computers, that's kind of a stupid thing to study. And then I've gotten smarter and smarter over the decades, because they go everywhere, right? How many computers do we use a day? Do we use 100?
I remember when I wished that everybody had email, but bad idea.
How'd that email thing work out? So RISC is not dead. You've got this RISC-V open source consortium. Has it had a commercial impact at this point? I have not been keeping up.
So RISC-V has been going on, I guess, since at Berkeley, since 2010, and I guess maybe 4 years ago we realized there was a desire for an open architecture. So it's moving up and to the right in terms of companies joining the RISC-V Foundation. I think we have 150. There was just a thing in the news about there's this phrase from IBM that IBM gets blamed for, which is FUD, for fear, uncertainty, doubt. There was a fear, uncertainty, and doubt webpage that was temporarily attacking RISC-V that some company may have put up there. So that's some kind of milestone. I think the public announcements is that NVIDIA said all of their chips are going to use RISC-V, which is tens of millions per year, and Western Digital has announced they're going to put RISC-V core in every disk, so bringing processing to the storage, and then that's going to be their future product line, so that's billions per year. And then presumably there's 150 companies involved, so that they're working on things that haven't been announced yet.
Yeah.
And in my opinion, open source has the possibility of changing business models, right? If we go back a few decades, open source software, was Bill Gates said it was the end of capitalism, right? Now Microsoft embraces it. But open source software fundamentally changed how software companies could operate, because they could download all the standard stuff and add their special sauce. And so if we can create the same thing for hardware, I think we can really accelerate innovation. And it's not just the instruction set. You're going to need the tool chain going forward. And it's not just, high-end microprocessors are the last place it'll happen. The first place it'll happen, I think, is lower-end wearables and things like that. It could be really exciting opportunities for new computers that don't look like computers.
Well, so, a couple of years ago, I ran into some crazy Russian guys in the Valley who were actually growing biological materials on silicon substrates, doing kind of an analog thing that you're talking about, but with actual biological material. Are there, optical, biological, quantum, is there a sort of a surprise that could come out of left field that's got nothing to do with CMOS?
So far, I've been pretty disappointed with how far the new ideas on that have gone, they have to both work in the lab and have to have a commercial way that they can get a lot better. And it's hard. Quantum computing, by the way, I think is a little bit overhyped in the short run. It's going to take a long slog and then be a big deal.
Yeah. We're running out of time, but there are two areas I'd like to pursue. One is China as a competitor. Are you guys aware of architectural innovation coming from China?
There's a group that's pretty excited about, they're one of the places that's doing hardware for machine learning, right? That's certainly one of the places that they're doing that. They're serious about building supercomputers. You know, they're building credible supercomputers today. So yeah, I would say they're among the leaders in that area. They're one of the leaders.
Yeah, I think it's going to be tremendous, and unfortunately, I think recent actions by the United States are going to encourage greater development of a domestic IT industry in China, up and down the stack.
Yeah. And just to sort of poll you guys, we talk a lot about weak AI. I noticed that there was a discussion of strong AI earlier today. Do you guys have strong feelings one way or another about artificial general intelligence? John McCarthy once in 1962 told DARPA he thought it would take about a decade.
Well, there's kind of the logic-based AI guys versus the machine learning-based AI guys. And what's in the newspapers today is the machine learning basis that we learn from data. I think that artificial general intelligence is way away, you know, like end of the century kind of thing, you know. It's hard to predict more than 5 or 10 years in this field. So when it's decades away, it's hard for me to worry about it.
Right. I mean, the key about the deep learning now is that you're learning from the data, so you only see what happens, and it's hard to do counterfactuals. Turing winner Judea Pearl has a really good book on this. You know, if all your data says that the rooster crowed and the dawn came, what do you say about if the rooster doesn't crow? You got nothing to say.
Yeah.
And you know, true intelligence requires things like that.
Final thought. Dave, I was watching your talk, one of your bad career talks, and at the very end you talked about, rather than personal wealth, you have a focus, and I was wondering if you could sort of lay that out. Have you made sort of consistent decisions throughout your career?
Yeah. It just struck me somewhere along the line. I was amazed I got to meet in my career millionaires, 10 millionaires, 100 millionaires, billionaires, 10 billionaires, and they weren't all that happy, you know. You know, you got to a point where you could have your own private airplane. Well, you don't have to wait in line at the airports. Well, that's something, you know. But it seemed like an alternative model was just to aim directly for happiness rather than aim for wealth that was supposed to make you happy. And it turns out our colleagues in psychology had this crazy idea about 20 years ago. Rather than study crazy people, let's study happy people and see what makes them happy. And so now it's a pretty well understood topic. If you go to, I think it's called Greater Good at Berkeley, they study and tell you how to be happy. But among the things there are, you know, having goals in your life, helping other people. The reason that you help other people, it actually makes you happy, whether you really help other people or not. You know, being involved in athletics, but having friends, you know. So you can study how to be happy. And so that's what I thought why don't I go directly to the goal? I'll aim at happiness. I'll let other people worry about it the other way.
I think those are words to live by. Please join me in congratulating Dave on his Turing.
All right, thank you.
Sure. Thank you, John, Dave, Mark. Thank you very much.
Thank you, Joe. Our next speaker will be the closing keynote at this design forum. Is a very special guest, and we are indeed very fortunate to have Bill Daly, who is the Chief Scientist and Senior VP of Research at NVIDIA. Dr. Daly joined NVIDIA almost a decade ago after spending 12 years at Stanford, where he was chairman of the computer science department. In an article he wrote in 2010, Dr. Daly proposed a quite controversial idea at the time that the end of Moore's law, and he suggested that parallel computing was the solution. And now we know that Dr. Dali was right and is right, and he certainly was ahead of his time. So he and his team have been the brains behind product architecture transformations at NVIDIA and industry in general in the area of parallel computing. Prior to Stanford, Dr. Dali was at MIT for 11 years and 4 years at Caltech prior to that. He won many prizes, awards, accolades, and honors. He's a member of the National Academy of Engineering, fellow of the American Academy of Arts and Sciences, fellow of the IEEE and ACM. He has received multiple ACM and IEEE awards, and he also holds more than 120 patents. So like you, I'm waiting to hear his perspectives on the future of computing. So please help me welcome Dr. Dali to the stage.
It's a pleasure being here, and I think as Dave and Mark said in the previous session, it's really a very exciting time to be a computer architect because now that Moore's law has kind of run its course, now we have to start getting clever to continue to deliver the value that people come to expect every few years out of their computing devices. And the means for delivering that value for the last several years, and I think for many years to come, has been through AI. And unless you've been hiding under a rock, you'll have noticed that there's an AI revolution going on in tasks like computer vision, speech recognition, natural language processing, and translation. Machines are now exceeding human capability. The graph on the left here shows progress on the ImageNet competition for image classification, which about 3 years ago exceeded human capability. And the human capability is not the average human. It's the human who curates the data sets. They actually know how to tell those 50 different species of dogs apart. And AI is not just limited to images. You're finding it everywhere. In the internet and the cloud, it's being used to improve your experience. In medicine, it's exceeding the capability of human radiologists to diagnose breast cancer and skin cancer. It's making it simpler for doctors to do diagnoses by mining histories of similar patients. It's driving entertainment by captioning images, translating languages. It's great for security. If you train a network on what's normal, it can find what's anomalous and spot suspicious activity. And one thing we're very excited about at NVIDIA is the prospect of saving a large fraction of the 1.3 million lives that are lost on the roads every year by applying AI to autonomous vehicles. To give you an idea of one thing you can do is by training a network progressively, starting with low-resolution images and moving up to high-resolution images. A team in our research labs recently were able to, using generative adversarial networks, be the first to synthesize convincing high-resolution images. These are images of celebrities generated by a network that's actually never seen an image of a celebrity. All it's been given is one bit of information from a discriminator network, telling it whether it was successful or not in faking the discriminator. Now, many people are concerned with this AI revolution that they're going to lose their jobs. But I'd like to convey to you my optimism about this, which is that AI is like a power tool. If you give a carpenter, power tools, a circular saw, a drill, an electric planer joiner, you don't take his job away, you make him more productive. And AI does the same thing. It's power tools for our brains. It takes us as humans and augments us to make us more capable at doing the things we're good at. AI will make doctors better doctors, more productive doctors. It won't replace doctors. It will take people in all walks of life and make them better at what they do. Now, what's particularly exciting being a computer architect is that this AI revolution has been entirely enabled by hardware. If you look at the 3 ingredients that feed today's AI revolution, which are algorithms, data, and hardware, the first 2 ingredients have been around for a while. All of the algorithms that modern AI are based on have been around since the 1980s. Neural networks, convolutional neural networks, backpropagation, stochastic gradient descent, all were developed in the 1980s, and there were small prototypes built in the 1980s. But there were 2 missing ingredients at that point in time. One was large labeled data sets. Those came about around 2004, 2005. There were million element labeled data sets available. Still, the revolution didn't happen. The final missing ingredient, the spark that ignited the revolution, was the ability of hardware that was powerful enough to run large models on large data sets in a reasonable amount of time. And so 2012, which is the year the ImageNet competition was first won by a deep neural network, was enabled by the use of NVIDIA GPUs. To train that network, it took about 2 weeks on NVIDIA GPUs to train AlexNet, which was the winner that year. Now, once the revolution was enabled by hardware, progress is now being gated by hardware. If you look at, as you want to improve the accuracy of a model, you have to do 2 things. One is you typically need a larger model, so it has more capacity. You add layers to the model. The layers may themselves get wider, more channels per layer. And then you also need more data. So it's this multiplicative product of data times model size that leads to a quadratic expansion in the amount of work needed to train that model. So for image recognition, over just a 3-year period, going from AlexNet to ResNet, there was a 16 times increase in the model size. And that would have been 160 times, but for the fact that one of the intervening years there, going from AlexNet to VGGNet, and then in 2014, GoogleNet, GoogleNet was actually a smaller model than VGGNet because it used a factoring of the network that separated the convolution by channel with the convolution in space. And so that otherwise would have been 160x over 3 years. In just 1 year for speech recognition, the Baidu, going from Deep Speech 1 to Deep Speech 2, took an order of magnitude more operations to train the network. This increase in computational demand is even more apparent scaling from one application domain to another. In some sense, image recognition, at least on ImageNet scale images, is relatively simple. It takes 7 exaflops to train ResNet on ImageNet. To train Deep Speech 2 takes 3 times as many operations, and to train the Google Neural Machine Translation Network takes another factor of 5. So going to more complex tasks also takes more demanding hardware. To give you an idea of an actual end application and demands, this is an excerpt from our self-driving car project at NVIDIA. We have one network that detects cars, another one that finds free space where your car is able to drive, and classifies what the boundary of that free space is. Another network finds lanes and suggests a path that keeps you within your lane. And then we can put all of these networks together, running the same images through 4 different neural networks. And we don't do this for 1 camera. We do this for 12 cameras situated around the car. So unlike a human driver that's only looking one direction at a time, our autonomous vehicles looking all directions at all times. And the networks are trained to work in any kind of weather, in rain or in snow, and to have a very high degree of accuracy at all of these. Let's look at the computation that it takes to do that. Running ResNet 50, which is by no means the most complex network. People have run ResNet 152 won ImageNet in 2015, and people have run networks with thousands of layers to get slightly more accuracy. But ResNet 50 is sort of our serviceable network that we use for many applications where we need a good compromise between performance and efficiency. Running it on one ImageNet image, a 225 by 225 image, is just under 8 billion operations per second. But of course, real-world images aren't 225 by 225. They're at least HD, and we're actually moving up to even higher resolution cameras in our cars. So to run 30 frames per second on ImageNet would be about a quarter of a teraop. To run 30 frames per second on an HD camera is just under 10 teraops, and we run 12 cameras, and we run 4 networks on those cameras. So you can get an idea of the hundreds of teraops required to do inference in an automobile. So how do we do that? Today, the best platform for doing AI is GPUs. And let me explain why and compare it a little bit to some of the special purpose hardware that you may have heard suggested by others. So the most powerful computing engine for training deep neural networks today is our Volta V100 GPU that we introduced about a year and a half ago. It's 21 billion transistors in TSMC's 12 nanometer FinFET technology. It's an enormous chip, over 800 square millimeters. And the important spec on this page is 125 teraflops of half precision performance in our Tensor cores. The Tensor core is sort of the marketing name for our half precision matrix multiply accumulate instruction, which is sort of the core inner loop of deep learning applications. To feed that, we have 32 gigabytes of HBM2 memory. Those are actually the 4 die on the silicon interposer around the large GPU chip in the center. And we have close to a terabyte per second of bandwidth to those HBM memories. And then we have NVLink channels with an aggregate of 300 gigabytes per second of NVLink to both connect these together and to connect them into host systems like an IBM Power 9 CPU. To put this in perspective, in 2002, the fastest computer on the planet was the NEC Earth simulator at 36 teraflops. The Volta V100 has, in terms of raw teraflops, 4 times the performance, although I am comparing the FP64 teraflops of the Earth simulator to the FP16 teraflops of Volta. Now, what gives it its core performance is taking the inner loop of deep learning and actually many linear algebra applications, which is a matrix multiply accumulate, and making this a single instruction. So our single instruction takes 2 input matrices, A and B, shown here in sort of blue and purple, multiplies them, this full matrix multiply, in FP16, and then accumulates the results into another 4x4 matrix in FP32, so no precision is lost during the addition. And it does that as a single operation. And what this does is it basically gives us all of the performance and efficiency of specialization while retaining the programmability of a general purpose GPU. There was a certain amount of debate when John Markov was discussing with Dave Patterson about the only way we're going to get more performance now is through specialization, and that's true. But you don't have to give up programmability to get specialization. You can specialize by building a specialized engine that does only one thing, or you can take a programmable engine and add specialized instructions to it. And what this slide shows is sort of the energy and the overhead of making your instructions coarser grained. Back in our Kepler generation, the biggest instruction we had to build deep learning out of was a half precision floating multiply accumulate. That takes about 1.5 picojoules. My energy numbers here I've doctored a bit, not to give away any secrets here, but they to scale are correct. And the overhead of issuing that instruction and fetching its operands and all was about 20 times the cost of doing the instruction. So that would not be a very efficient way to build a deep learning machine. By Pascal, we had a 4-element dot product. So you could take 4 numbers, multiply them together, and sum the results. And now our overhead is only 5x. And moving on to the Volta generation, we're now doing 128 arithmetic operations with a single instruction. So it's 110 picojoules of arithmetic energy. The overhead energy is now less than 30%. And so if you did nothing, if you basically build a chip to do nothing but matrix multiplies, you would not beat the energy efficiency of Volta by more than 30%. And that 30% is a very small price to pay for the programmability of having a fully programmable GPU that you can use to program new machine learning algorithms as they become available. Now, because people to train these larger networks need something more powerful than a single GPU, we developed our NVLink technology and most recently NVSwitch, an 18-port NVLink switch that can be used to connect GPUs together as if they were one big GPU. They share memory. They can do loads and stores to the memory across the entire machine. And at our GTC conference this May, we announced our DGX2 box, which is 16 Voltas connected together with 24 NV switches with very high bandwidth, basically 300 gigabytes per second from any Volta to any Volta. To put this in perspective, the DGX2 box is 2 petaflops of FP16 performance. Going on the top 500 list, the fastest machine in the world in 2010 was the Cray Jaguar at Oak Ridge National Laboratories at 1.76 petaflops. So we are basically as powerful in peak flops as the fastest machine in the world 8 years ago in a box that's basically the size of a dorm refrigerator. And if you wanted to compare the FP64 flops, it would take 8 of these boxes to be a Jaguar. So it is in fact this basic technology of Voltas with NVLink that is now powering the fastest supercomputer in the world. This is the same one that John Kelly mentioned in his talk this morning. The Summit machine at Oak Ridge National Laboratories is the head of the top 500 list right now. It is about 200 petaflops performance, and something like 99% of those 200 petaflops are coming from the 27,600 Volta GPUs that are in Summit. The Power 9s are basically the traffic cops that steer the data to and from the Voltas. And one way I like to think about the Summit machine is everybody talks a lot about building an exaflop machine. Summit is an exaflop machine. It has over 3 exaflops of FP16 performance. And some of the work that Jack Dongarra at the University of Tennessee has done using mixed precision has been able to sustain over an exaflop on actual problems by leveraging the half precision along with the single precision and double precision performance. And so real science is being accelerated by this, and it's also the most powerful AI machine in the world at this point. At the other end of the spectrum, to power things like video surveillance cameras and self-driving cars, we make our Xavier SoC. And Xavier is smaller, but it uses the same technology. It has 512 Volta CUDA cores, and that's 1/10 of the 5120 that's in the V100. But it also has our deep learning accelerator. For embedded applications is where you do want to build dedicated accelerators for deep learning, where you want to squeeze that last square millimeter of area out and that last 30% of energy. And so we open sourced our deep learning accelerator because what we discovered is to build an SoC, the SoC has to be specialized for whatever vertical you're designing it for. And so we're very much pursuing robotics, intelligent video analytics, and self-driving cars. But for many other verticals, we want to empower other people to build out the AI ecosystem. So we've open sourced the NVIDIA DLA. You can go to nvdla.org, download the RTL, download the software for it. It's completely supported. And it's very much like a Google TPU in that one of the boxes in the middle here is a big matrix multiplier array, but it has 2 things that you won't find in a TPU that make it significantly more powerful. The first is support for sparsity. It turns out that most neural networks are sparse, both the weights are sparse and the activations are sparse, and so we have support for that, so you get much more energy efficiency than if you actually did all of the multiply operations. And then we have support for what's called Winograd transform, because if you're doing a convolution operation, if you do it in the normal domain, you know, a 3x3 convolution takes 9 multiplies per point. If you do it in the transform domain, it's 1 multiply per point. So this winds up being a very efficient deep learning accelerator. If you look at the alternative ways of carrying out inference on different platforms, CPUs are horribly energy inefficient because they have this huge overhead of fetching and decoding instructions and rescheduling them out of order on every instruction. FPGAs are just bad ASICs. They typically are down about a factor of 100 in both area and power. If you use the LUTs, if you use the hardwired logic, they're great, but using the LUTs, they're about 100 off of what an ASIC can do in area and power. Going from Pascal to Volta, we basically eliminated the performance disadvantage of a programmable GPU by making the instruction we're accelerating big enough that we completely amortize out the overhead. So going to the DLA is only about a 30% gain in energy efficiency. So what are the prospects going forward to do even better on efficiency for deep learning? Well, the first thing, and John mentioned this in his talk as well, is precision. So if you look at the cost of operations, deep learning operations tend to be dominated by multiplies. The energy of a multiply goes quadratically with the number of bits. So doing an 8-bit multiply takes not 1/4 the energy of a 32-bit, but 1/16. And so driving down the precision saves us an enormous amount of arithmetic. Even more importantly, driving down the precision makes the data set that we have to store for both weights and activations smaller, allowing it to fit in a smaller memory. And like real estate, designing a chip, location is everything. The RAM right next to your arithmetic units is extremely valuable real estate because you can access it with really just the native access energy of the SRAM mat, about 5 picojoules per 32-bit word. If I have to reference it somewhere else, say 10 millimeters away on the chip, it's 50 picojoules per word. The actual SRAM access is the same, but now I'm paying an additional 45 picojoules to traverse the wires to get from where I accessed it, and the wire energy starts to dominate. If I go off chip, it's yet another order of magnitude worse. So each time I can get sort of a degree of locality, I get an order of magnitude energy savings. So making the models and the activations small helps a lot in crunching this down. So how far can you go in terms of precision? These graphs show some studies I did with a few students at Stanford, where we showed that for fully connected layers, you can drop down to 4 bits per weight with no loss of accuracy, and you can go down to 2 bits before you really fall off a cliff. And hypothesis we have that we're still testing is that if you go down to that 2 bits where you've lost a couple % accuracy, you can get that couple % back then by augmenting the network, making it a little bit deeper and a little bit wider per layer. Similarly, for convolutional layers, it's the same story, but at 6 and 4 bits. No loss of accuracy to 6 bits, and then a very slight loss of accuracy at 4 bits, so we suspect that you can get back by augmenting the network. So there's definitely room for precision reduction to get additional efficiency. The other way of getting efficiency is through pruning. So it turns out that human brains do this. You've had the most neurons you ever had in your life when you were 1 year old. And ever since then, it's been going downhill. But actually, it isn't really downhill. Your brain has been tuning itself. And in that process of tuning, it's actually been eliminating neurons. And it turns out that we can do the same thing with these artificial neural networks by taking the neural network, finding out which neurons aren't really carrying their weight, kind of like doing your focal review every year and managing out the bottom neurons. And then we basically retrain the network to have the other neurons learn how to do the stuff that those neurons that aren't around anymore were doing. When we do this, what we found, this is a graph from our 2015 NIPS paper, is that we can throw away 90% of the neurons and have the same accuracy we started with for fully connected layers. We can throw away 70% of the neurons for convolutional layers. And in fact, this is such a powerful regularization technique, we can use it either to reduce the size of the network or to improve its performance. Because if we do this process iteratively and grow the neurons back, we actually have a network that's more accurate than we had before we started. The final thing we can do is use more accurate network, or more efficient network architectures. So GoogleNet was one step in this direction. This chart shows SqueezeNet, which was a project that I did in collaboration with some colleagues at Stanford and Berkeley, where we basically factor the network. So we squeeze the number of channels down before we do the expensive 3x3 convolutions, and then expand them back up to combine the information between channels. And if we do it this way, we wind up with orders of magnitude less space. So here, we're able to keep the model size at 0.5 megabyte and get the same accuracy that AlexNet got with 250 megabyte model size. So let me now talk about some application areas that are sort of near and dear to me working for a company that's primarily in computer graphics. A lot of people don't appreciate it, but the gaming industry is actually bigger than the motion picture industry by revenue. I think that they need to run their own Oscars or something, get better PR so that people appreciate that. And putting out a AAA game is often a billion-dollar enterprise. You know, people will invest $1 billion in production costs, and most of that money goes to pay artists. And the game studios are almost completely artist time limited. It's not engineers, it's not programmers, it's artists. And so the critical thing you need to do is to make the content easier to produce. So as an example of that, consider the task of automating a character in the game. Typically, this is done by having an actor go up on a motion capture stage, doing video performance capture, and then having an artist take a rig, which has something like 300 control points that then project down to controlling about 5,000 vertices on the face to characterize the animation. That's what's shown on the left side of the video I'm about to play. On the right side, we trained a neural network to go just from the audio stream and animate the face, all 5,000 vertices directly without a rig. And tell if you can tell the difference. Let me play the video here. The audio is turned off.
This is our main objective. Alexei, you and your men will do that. You have to go in and out very quick. I want you to get all the ammo and weapons that you can carry and come back as quickly as you can. You understand?
So in double-blind experiments, people cannot tell the difference between the two, and it saves several hundred hours of artist time in just the clip I just showed you. Another place where you spend a lot of artist time is in characterizing materials. Suppose I have a leather material like this that I want to put in a scene. It typically would take an artist a lot of time to build the assets that are required to make a shader to produce this material. What this video shows is that with a single iPhone photo, we're able to take a neural network and then produce the 4 shader assets that are shown on the right side, the diffuse and specular albedo, the glossiness, and the surface normals. And then from those, I can play the video. I don't know if this thing goes backwards or not. Can I play that video again without advancing? If I can play that video, I move the light source around, and I'm basically reshading the leather surface just from one iPhone photo. Otherwise, yeah, this is the one. Just play the video. Nope, I guess not. Okay, we'll move forward. So in that case, I again saved what was probably a week or 2 of artist time creating the material assets to model each material. And in a complex scene where you may have a lot of different surfaces with different materials on it, that's an enormous amount of content time. So content is part of what AI can do for graphics. Another part is in rendering. So if you want to know the real difference between the quality of graphics you see in a motion picture, whether it's an animated picture, say by Pixar, or a live action film, that has CG in it, The difference is in real-time graphics, we have to produce an image every 16 milliseconds. In the motion picture industry, they will often spend a half an hour on thousands of compute nodes producing a single frame. And the way they do that is using a technology called ray tracing. It's basically doing a physics simulation of the light transport. You cast light from every pixel of the camera, you see what it bounces off of, but it's a Monte Carlo process, right? If you hit a diffuse surface, it can bounce in any direction, and you need to sample those directions with enough points that you actually hit the light sources or you hit the bright surfaces that they're going to scatter off of next to produce an image like the one on the right. So what this image shows is on the left side, we've done the ray tracing calculation, but we've done it with 5 rays per pixel. And so it gives you a very grainy image. It's as if you shot a photograph in very low light. You get that graininess of the film or of the image sensor coming through. The right side of the picture looks as if we did a motion picture level image with 10,000 rays per pixel, but in fact, it is the image on the left run through a neural network to filter it, and so we can clean it up. And by doing this, we're able to render very high quality images 2,000 times faster than they otherwise would have been able to do. And this holds the promise, we're not there yet, this is still very much a research project, of being able to do real-time ray tracing to produce motion picture quality images in your video games. So let me wrap up here. It's a very exciting time in the semiconductor industry and the computer industry, because AI has only really scratched the surface in terms of applications. It's pervading every aspect of human life and is going to go a lot further. Already it's very prevalent in transportation, and I think it will become more so as we move into a world of autonomous vehicles. It's revolutionizing healthcare. It will give us both higher quality healthcare at lower cost. It'll be power tools for the doctor's brains. As a longtime educator, I'm very excited about its applications to education, where potentially we can produce a personalized tutor for every individual that understands how to motivate that person, what they're excited about, and how they learn, so it can deliver the material in a way that's meaningful for them. And of course, it will help us do better graphics. As a computer architect, I'm particularly excited that hardware has enabled this revolution. Of the 3 ingredients needed for AI, the algorithms, the data, and the hardware was the one that was the last to arrive and sparked the revolution. And today, I feel a lot of pressure to continue to deliver hardware advances because it's pacing the revolution. People would like to use bigger models on larger data sets, do more complex tasks, and they're very much limited by the hardware they have to run on today. Today, the best hardware you can get to do these tasks are GPUs and fixed function accelerators. Today, the GV100 is 125, this slide needs to be updated, 125 teraflops, half precision, 400 gigaflops per watt. So think about it as 3 times the fastest supercomputer in the world from 2004. You take 16 of those, put them in a box. The DGX2 is 2 petaflops of half precision. It's basically comparable to the fastest supercomputer in the world from 2010, but in something the size of a dorm refrigerator and consuming merely 10 kilowatts. Xavier, for things where you need more like a 10 to 30 watt envelope, is 30 teraflops of deep learning performance at 2 teraops per watt. There's a lot of prospects for us to become even more efficient going forward by reducing the precision. At 8 bits, we have 16 times the efficiency of 32 bits for multiplies. And I'm actually very optimistic about some hybrid formats. I've been experimenting in the labs with 3 and 4-bit exponent-only notations that seem to work extremely well. And then we can prune out our networks for fully connected layers and recurrent networks. Typically, you can throw 90% of the weights away, and it turns out that about 70% of the activations are 0. So 97% of the work doesn't have to be done if you can exploit sparsity. So sparsity is a hugely powerful way of continuing to scale things. Because somebody said we need 1,000x. Well, there's 30x of that 1,000x. That's half on a log scale of what you need is just by exploiting the sparsity. And then by using very efficient models, we can close the gap and build even more powerful AI to solve some of society's most pressing problems. So thank you very much.